see here. I'm using the browser, so
okay.
Things are a little bit different.
I think that as a sort of presenter or moderator, I think I'm not able to raise my hand. There.
Okay, I see Steve
got raised. Yeah.
Okay, got it. So the people in the browser like me, I don't think we have a raise hand function, but I can see it. So that's good.
Okay. Okay, so folks in the browser can just use the chat if they great. All right, I'll give people another minute to join. Looks like people are trickling in. I'll give people another minute or so before we dive in. All right, we'll go ahead and get started. Welcome, good morning, and welcome to the Software Engineering Working Group session. I'm one of the co-chairs of the Software Engineering Group, Bill Sachs from NCAR CGD. The other co-chair is Ligia Bernardet from NOAA. Ligia, do you want to say a brief hello for those who don't know you?
Hello, everybody. Well, I am Ligia Bernardet from NOAA Global Systems Laboratory here in Boulder, Colorado.
So we have a good agenda that I'm looking forward to this morning. Just a couple things I want to highlight here. The last half hour or so will be devoted to an open discussion. So we can use this time to have a more extended discussion that emerges from any of the talks this morning, or really to discuss any other topics that the people would like to discuss in this group. And then following that, we are planning to keep the Zoom session open from 12 until 1, all the way until 1 o'clock Mountain Time for just a sort of informal networking and conversations over lunch. So we hope you'll stick around and join us. It's always a little hard having these remote meetings, so hoping to have some recreation of some actual socializing at that time, so we can catch up and chat. Just a few logistics. The meeting is being streamed to YouTube and recorded. Depending on whether there's sort of interesting things in the chat, we might also record the chat, in which case I believe that also records private chat. So don't put any, don't arrange your next date in the private chat here. For questions, you can either use the raise hand feature on Zoom or type your question or comment in the chat. I know people who are on here with the web-based interface to Zoom, I don't think have the raise hand feature, so you can use the chat if you have a question for the speakers. And then speakers will give you a 2-minute warning at the 16-minute mark, though you can let us know if you want a kind of earlier warning as well. And then one more thing, some of us are going to go this evening to the Rayback Collective in Boulder, meeting around 5:15 p.m. To just socialize, have some dinner. And so we hope if you're local and able to, we hope you can join us for that. We hope to see some of you there. And then finally, just to remind you of the NCAR Code of Conduct that applies during this meeting and all other meetings. So please try to offer constructive feedback, share the air, acknowledge teamwork, encourage innovation, show appreciation, and consider new ideas. So with that, I will stop sharing and turn this over, and we'll get started with the exciting series of talks.
All right. Well, thank you, Bill. So welcome, everybody. Good morning. I'm going to be sharing this first part of the talk, so up until the break. And we're going to start today with Mariana Vertenstein. She's going to talk to us about an update on ESMF NUOPSI coupling infrastructure in CESM. So she has a longer time slot And we are going to give Mariana a 20-minute warning and then a 26-minute warning so that we can fit the talk and the Q&A within the half-an-hour slot. So you can share your screen, Mariana.
Okay. Great. Can you see this, Leisha? We tested this beforehand.
Yes,
Yeah.
It looks good.
All right, great. So I think that given the variety of stuff I'm talking about, if there are questions in the chat that are relevant to a given topic and there's some confusion, please just stop me. I'm happy to answer it because I do have some more time, and so we can spread out some of the questions. Sometimes it's hard to get them all in at the very end. So what I want to talk about is what I believe is the transformative capabilities, at least this is in my opinion, of the new coupling infrastructure we have to enable new science to be done with CSM, and also to enable completely new collaboration with modeling efforts, not just in the United States at NOAA, but also with two European efforts that are also using CSM. And I'll have some details of this coming up. So the outline is very terse, but there's a lot of information that's coming in each of these bullets. So the first thing I want to talk about is how we communicate information between components with this new coupling infrastructure. I think some of you have already seen some of these presentations, but I'll be talking about some of the new milestones we've achieved with this new coupling infrastructure, which is called CMEPS. And I'll try to get all the acronyms defined. One thing I think is extremely important is enabling an infrastructure that has the capability to do what I call hierarchical modeling development, which is the ability to selectively turn off feedbacks and isolate the parts of the system that you're most interested in developing with your science. And that's at least to some extent enabled by the data models we have, the new data models which are the community data models for Earth prediction systems, or CDEPs. And then I'll wrap up with what we're trying to do to address the challenges of ultra-high resolution simulations, particularly our collaboration with Earthworks right now. And I'll summarize finally with the new ESMF release. That's the Earth System Modeling Framework that we're using that addresses some of the bottlenecks that we found when we tried to start up these ultra-high resolution simulations. So first, how do you enable the effective communication of components with each other? So as you all know, the CSM model has what we call a hub and spoke architecture. Components exchange boundary data. Currently, it's still two-dimensional boundary data with a central mediator, which is this hub called the new OPSI Community Mediator for Earth Prediction Systems. And that hub, the CMEPS, is targeted to be able to grid data from a set of source component to your target component, merge that data using the fractions that are needed to merge, say, data from ice, ocean, and land to the atmosphere, as an example. And also it carries out atmosphere-ocean flux calculation, downscaling of data from the land ice component, and so on. The key part is that to be able to communicate with CMEPS, each component has what's called a new OPSI cap, which is just a very lightweight translation layer that takes the data structures in the source component, translates it to ESMF new OPSI. New OPSI is simply a layer on top of ESMF that enables standardization of coupling between components in terms of building an Earth system model. And this translation layer simply takes data from the component, translates it to ESMF new OPSI, and then the mediator can act on it with via sending it via the connectors, these lines here. And then when you get data back to your target component, you need to translate the data structures from ESMF new OPSI back to your data structures for your component. And that's all that the cap does. Sorry, I went. So this is a very busy slide, but it contains a lot of the updates that we've done. So in this slide, what I'm trying to show is that all of these are the prognostic components that are being used not just by CSM, but other modeling efforts. So if you look at CSM and you look at what the components are for CSM, it has size 6, MOM 6, WaveWatch 3, CESM, Mozart for the river, and a new component called MisiRoute, CAM, and CTSM. And what you see here in the gray shaded ovals are that those components, size 6, MOM 6, and now WaveWatch 3, are actually being shared directly with NOAA. We have a shared CAP and we have shared development efforts. So the strength of this is that when you take a prognostic component and you actually have more than one modeling effort using it, you're testing it in a new various scientific configurations. And so you have much more robust testing and trust in the development of new science in that system. The other thing to point out is that the other bullets in colors, such as the ocean, MPAS-O, NEMO, and BLUM, are really being used by other modeling efforts. MPAS-O, the MPAS Ocean, is being used by Earthworks. NEMO is being used by CMCC in Europe. BLUM is being used by Norreas and Norway, and they're using this exact same coupling infrastructure. Similarly, the bullets in red for UFS-ATM and the land model NOAA and PNLM4 are land-specific components that are being used by NOAA. So what you have here is a coupling infrastructure that truly enables interoperability between several modeling efforts, and there is interest to go past this, particularly there's interest from the Navy to potentially use CMEPS in their modeling system. The key point that is different between NUOPSI CMEPS and our old coupling infrastructure is that CMEPS is a component that is identical in functionality to, say, the atmosphere component. It is its own unit and can be shared. What's different, and I haven't shown on this slide, is the drivers that drive this whole system. Those drivers are very lightweight, and they drive the temporal evolution of the system, and those are model specific. So the only difference between these various component utilizations is the drivers that are there. And of course, what we also have is the ability, and I'll talk about this a bit later, to swap out prognostic components for data components in these various scenarios, and that enables you to selectively turn off feedbacks in the system. And that is very powerful for being able to do hierarchical model development at the component level, where you will drive, say, CAM with a data ocean or a slab ocean. So we have written a completely new set of data models that I outlined briefly last year called the Community Data Model for Earth Prediction Systems that is NUOPSI compliant, and that is CMEPS compliant, and that has a lot of new functionality that will be very powerful, both for sharing with other modeling efforts and for also being used within the component to ingest forcing data. So what are some of the benefits of CMEPS? For one, it's easier to introduce new grids. One of the things that ESMF NUOPSI does that is a real big change in the system is that it does online regridding. It creates the route handles, so the mapping weights between a source component and a destination component. It creates those at runtime in parallel. So before, when we were using our old coupling infrastructure for a fully coupled pre-industrial run, you needed to create offline 25 mapping files for a set of combinations. Now we are down to 4, and the reason it's 4 is that these are runoff to ocean mapping files that need to be customized. And at some point in the future, ESMF is very interested in creating those. But imagine all of the overhead you need to do, not just to create the mapping files, but to put them into the scripting system so that you would know, so it's disk space, it's scripting complexity. And so it made the generation of new grids extremely cumbersome. Another new addition is that when you introduced a new grid, you also needed to create offline land fraction files, because basically the fraction that is land on the land grid is obtained by mapping the ocean mass, which is 1 or 0, conservatively using first order interpolation to the land grid. And so in addition to creating the mapping files, you also needed to do this. So before, each new component grid required generating offline fraction files, again, putting them in the scripts, figuring out how you were going to access them. So now what we have is inside both CDEPs and the CTSM CAP, these land fraction files are generated at runtime by conservatively mapping the ocean mass to the land fraction. And so you no longer have to do this. Again, a really great simplification. This is hot off the press, but this doesn't relate directly to CMAPs, but it relates to, sorry, I don't know why this is happening. Okay, it relates to the ability to introduce new grids by having a completely new land surface data set generation. So before, when you introduced a new grid for the land, you needed, as part of that process, to create 17 offline mapping files. And then use those mapping files into a surface data set generation code that only ran on one processor. As an example, as we were going to higher resolutions, this took more and more time. One metric is that it took over 2 days to generate a surface data set at 7.5 kilometers for an MPAS grid. Now, we have a completely new land surface dataset generation tool using ESMF Nuopsy and Parallel IO, which has totally changed this. So we can create the same MPAS surface dataset, but it takes 10 minutes. So you do need to use a lot more processors, but you now have scalability. And basically, some of the new raw data sets that encompass the 17 before offline mapping files are getting at higher and higher resolution. So one of the challenges we had is that how could you have mapped a 30-second soil texture data set that have 724 million points to create a new surface data set? You couldn't before. You were reaching a bottleneck. Now we can do it. So also, we are leveraging an ESMF dynamic masking, which is this great capability that can be used not just for mapping, but also for doing things like calculating surface standard deviation of surface elevation statistics. So I think those three things are outlined where I think that ESMF and Nuopsy and CMAPs are real game changers for what we can do. So this is a science change. So what we can now do, and I think Bill Lips can outline this briefly in his talk, is that we have some new capabilities for land ice simulations that simply were not available before. One of the things we've wanted to do for a long time is enable both Antarctica and Greenland to run simultaneously in simulation, and potentially a whole other set of glaciers that could be added. So before, what the proposed approach was to create a unified global grid. And that meant that for every combination of grids between Antarctica and Greenland, you would have had to create a new global grid, which would have resulted again in a combinatorial explosion of grid combinations and files. What ESMF permits us to do is actually very simply in the CAP to create a nested state, where each ice sheet in CESM that has its own mesh couples directly to a corresponding ice sheet in the mediator. This is very extensible, user-friendly, and easy to see because all of the complexity is hidden in the ESMF library. And so not only can you run Greenland and Antarctica in one simulation now, but we have the capability in CMAPs to add an arbitrary number of ice sheets that can be coupled at runtime now. And we have carefully validated this. A lot of this work has been done by close collaboration with Bill Sachs. And so I think, again, Bill Lipscomb and his group are extremely excited to be able to do this. But in addition to this, we can also enable Antarctic ocean coupling. The challenge with this is that you need to have ocean land ice coupling at multiple ocean levels, where each ocean level has a different bathymetry. What you encountered before as a prototype is that in addition to the component mapping files, those 25 mapping files, you had to create another mapping file for every ocean CESM mapping that had a different bathymetry level. With ESMF dynamic masking functionality, that's all gone. And so all you need to know is what the bathymetry is, and the dynamic masking enables you to do that regridding seamlessly in CMEPS at runtime. So you only need to pass in one field from the ocean to the CMEPS, where the multiple levels are contained in what is called ungridded dimension, and you have this new Antarctic Ocean land ice capability. Another that we're able to do is do computational efficiency using this new ESMF managed threading. And basically the idea is that if you had a component that was threaded 4 ways and another component that was not threaded before, if they had to share the same nodes, then the second component, component B, could only use 1/4 of the nodes in a node. So that led to a lot of idle cores and poor HPC resource utilization. So ESMF last year has introduced a completely new capability called managed threading. So if component A is threaded 4 ways, component B is not threaded, they can now still use the same nodes, and component B can use all of the cores in the node, thereby, greatly increasing the efficiency of the overall system. And what you can see below is that this not only gives you greater efficiency, it also gives you greater throughput. And we have just not had the time over the last year to actually implement this in all the scripting system, but I want to point out that it's there, and it's a high priority for us to try to get working out of the box as we move forward. In terms of atmosphere ocean flux calculation, we have a completely new capability that I think will greatly facilitate scientific development, particularly if the ocean and atmosphere ice grids are at 2 different resolutions, and that's using what's called the exchange grid. So basically, the exchange grid is simply the union of a target and destination grid. So you can see here in grid A, you have a fairly coarse grid. In grid B, you have a much finer grid. And finally, the exchange grid, which is C, is simply a union of those 2 grids. And what we've put in CMEPS is the ability to do atmosphere ocean flux calculation on any one of these 3 grids, but the right grid to do it on is the exchange grid, and that will be the default way of doing it. So what does this imply? So thanks to Adam Harrington for showing how this worked initially in a tropical cyclone case. And the main idea in tropical cyclone tests is that what you want to have when you look at the stresses between the atmosphere and ocean when you are running a very high resolution atmosphere, say a 1/4-degree spectral element with a 1-degree ocean, is that you want the stresses to align with the winds. And what's happening here is that when you calculated the atmosphere ocean fluxes on the ocean grid, this was simply not the case. And so you had to figure out how to calculate this on the atmosphere grid, which meant that every time you were going to do a simulation, you needed to figure out what is the best grid to calculate this on. And what about a simulation that had a refined grid, where in some areas you have very high resolution ocean, maybe less resolution atmosphere, in other areas it's just the reverse. And so doing everything on the exchange grid takes care of that. What you have here is an excellent example of the latent heat flux that's mapped to the atmosphere grid when you do the calculation on the X grid. And you can see here on the left, when you do it on the ocean grid, you get a very blocky structure. So this is now in CMEPS. Extensive simulations were done, including coupled 100-year runs, and we have been given the go-ahead to have this be the default, and that is what's going to happen. So I just want to add that it's not just us that's looking at the exchange grid. NOAA, the seasonal system, has explored using the exchange grid because currently they were doing their atmosphere ocean flux calculation in the atmosphere. And this enables you to actually bring it into the mediator, parallel to what we're doing in CSM. But in addition, what Ufuk Turunçulu has done is that he has brought in the ability to use different science for calculating the atmosphere-ocean flux calculation using this and treating the mediator, CMEPS, as a host model for the CCPP framework. Dom will talk about this a bit later. But what this enables you to do now is have various atmosphere-ocean flux calculations that can be explored all using the exchange grid, which is the correct grid to use, both for refined grid and for regardless of the atmosphere ocean flux resolutions when you're doing it on two different grids that are very different, even if they're not refined. And finally, we're looking at new capability in CEIS. We have a new
excuse
default.
me, this is your 20-minute warning.
Thank you. Okay, so we have a new default ICE component, CEIS 6, that's coming in. We have new WaveWatch 3 capability, which is that we've now brought in a completely new wave component that is at the head of the wave development effort at NOAA EMC. We are sharing this code with EMC, and it's going to be the default in upcoming CSM3 development tags. So this brings in not just the capability of having provenance and collaboration and new capabilities, but the ability to explore new functionality that we simply couldn't do before with our old WaveWatch code. In addition, we're looking at new WaveWatch 3 CEIS coupling because you need that because the wave fields break the sea ice into smaller flows. Sea ice concentration then feeds back to the wave fields. And so what we're trying to do is send 25 new spectral data fields from the wave to CEIS. And with ESMF New OPSI, you don't need to send 25 separate fields. You can actually pack all of these into one field that has what's called a distributed dimension for all the 25 fields. So again, this is just another way of greatly simplifying coupling that would have been much harder to do before. And finally, this is just very brief. We are supporting CSM to do DART ensemble Kalman filter data assimilation. I haven't shown that yet, but that is being worked on to validate. But at the same time, we're working with the JEDI group, which has a new operational data assimilation system to create a layer on top of the new OPSI driver that would enable coupled data assimilation via sending three-dimensional states to the JEDI model and thereby permitting a path forward to do coupled data assimilation. This would not apply to ensemble Kalman filter, but it would apply to data assimilation where you're using 3D var and potentially 4D var. So in terms of a hierarchical model development, what we'd like to do, if you see here, this is a slide for increased complexity. We would like to be able to selectively turn on complexity and feedbacks easily within our whole coupled model system. And we can do that at least partially by having a new set of data models, which we call CDEPs. They are ESMF compliant data models. The key point is that with these data models, and this was true with our old data models, you're able to ingest multiple data sources where each have completely different spatial and temporal resolutions and also customize how they are handled. The key point is that all data is read in with parallel I/O. And now you can easily ingest both 2D and 3D forcing fields. But now, unlike what was done with Coupler 7, at runtime, you have automated regridding capability. You can do online regridding of the data you ingest, both on 2D and 3D fields. And you have support for different regridding types, such as conservative and patch and various time interpolations. What's also new is that we are trying to we have an online interface for CDEPs where the prognostic components can call the share code in CDEPs that does the time interpolation and online regridding directly from its component. And that's starting to be increasingly used throughout the system, say for getting nitrogen deposition read in the atmosphere, new OPSI cap, and so forth, and extensively in CTSM already. So the collaboration with new in NOAA, who is using CDEPs now in its operational system, is that we have brought in a whole new set of data forcings, particularly for the atmosphere, that test and enable CDEPs to run with many new forcing scenarios that simply we couldn't do before. So this is the strength of having community software that is used by more than one modeling system. They bring new functionality in and test it in totally different scenarios. So what you have is a much more extensible and robust system. You can see here all of the components that are currently ocean components on the left that are being tested and routinely run with CDEPs. So in terms of where I'm going to switch from hierarchical model development to ultra high resolution, I think in the atmosphere model working group yesterday, the Earthworks project was presented. If you didn't hear that, what it is, it's a 5-year NSF-funded university-based project to develop a global coupled model. And I want to stress based on CSM because it doesn't have all the CSM component, but it does have the CSM coupling infrastructure, CMEX, and it will use CDEPs. And the key thing is to target a single uniform MPAS 3.75 kilometer global grid for the atmosphere, ocean, sea ice, and land surface. And for this point, you're going to be using a non-hydrostatic dynamical core in MPAS, but it will be run via CAM. So you're not running the MPAS atmosphere, you're running the MPAS dynamical core in CAM. The MPAS ocean is what's going to be used in terms of being able to run in the MPAS grid. We have an MPAS sea ice model that is analogous to size 6, but it has a different dynamical core. It will use CTSM and of course CMEPS. So now we're taking CMEPS and exercising it in ultra high resolution configurations. And we ran into some problems when we started doing this, which is what's
Mariana,
great.
26 minutes. So
Okay,
2 more
I've only
minutes.
got 2 more slides. Okay,
thank you.
Thanks, Alicia. So ESMF we encountered problems with memory scalability in terms of ingesting the grid for this ultra high resolution, and we ran into several other memory bottlenecks. And we worked very closely with the ESMF group that created an ESMF 8.3 release on June 8th. And basically the main features of this release that were applicable to us is that we now have a scalable mesh creation from the file. This was done very closely in collaboration with Jim Edwards and Bob from CSEG and Bob Ohnke from the ESMF group. So we now have scalable mesh creation. And the parallel IO library that is used inside ESMF was an old PIO library. It has now been migrated to PIO2. And lots of other memory scalability has also been addressed. And so suddenly we can now run 7.5 kilometer runs with no problem. And we're looking at now, of course, 3.75 kilometer runs and seeing other memory issues, but they're no longer within the ESMF category. And that kind of encompasses a very brief outline of what we've done over the last year, and I really welcome questions. Thank you. Oh, one more thing. I want to really thank, I didn't mention the detailed list of people that have helped in this because the list was getting very long, but I do want to have a call out to the ESMF core team, Jim Edwards, Ufuk Tarantula from ESMF, and Rocky Dunlap, who really, and Bill Sachs, who stepped up to get some of these features in place.
Thank you so much, Mariana. So we have time for 1 or 2 quick questions. So if you have a question, please type it on the chat or raise your hand. And then you will be able to unmute and ask your question. I don't see any questions yet. Oh, here's one from Frank Bryan. Frank, can you unmute and ask your question?
Yeah. Hi, Mariana. I was wondering, does the exchange grid work for component models that do not have quadrilateral meshes?
Yes. It works for unstructured grids. It works for any mesh. Oh,
that might
quadrilateral.
result in
That's
very
a different
weird geometry
question.
of the subcells. You have a
Yeah.
triangular mesh
Sorry.
ocean and a quadrilateral mesh atmosphere. Does that work?
I think the answer is yes, but I have to check with Rocky. I'm trying to understand I'm trying to remember the limitations, the mesh that are limited, but I'll get back to you on that, Frank.
Thank you.
All right. Any additional questions? Jim, you have your hand up.
Yeah, I just wanted to clarify something that Mariana said earlier about the ESMF aware threading. That does work out of the box. It's ready to go.
Right. I guess what I meant is it works out of the box, but it doesn't automatically get set up for you.
Right. You have to set it up.
You have to set it up. So it works, but it's not user friendly quite yet. Not to the extent that the other layouts are.
Okay. I see Steve has his hand up, but we are at time. So I'm going to ask Steve to move his question to the general Q&A session at the end. And we're going to move on. Thank you, Mariana. And our next speaker is Dom Heinzeller. And he's going to talk to us about the Common Community Physics Package, CCPP update. So Mariana, you can stop sharing.
I'm trying to find out where my stop sharing. Oh, here it is.
And
right.
Dom, you can share yours.
All right. Can you hear me?
Yes, I can. I can see some mountains.
Okay.
Okay, looks good now. Thanks.
All right. So good morning, everyone. On behalf of the CCPP developer team at the DTC, I want to give you a brief update and summary of the Common Community Physics Package. I've talked to this audience before, but to refresh your memory, this is a bit of a history of the CCPP. The work on it started in 2017 to develop the future UFS infrastructure for atmospheric physics. So the goal behind this effort was to facilitate the improvement of physical parameterizations and their transition from research to operations. The idea is to make it easier to add new schemes, modify them, or transfer them between the different models. So CCPP consists of 3 different packages: an infrastructure component, the framework, a library of compliant parameterizations, the physics, and then comprehensive documentation. And here on this image on the right from Rocky, you can see the CCPP in the unified forecast system, and we'll discuss this in a little more on the next slide. What I wanted to say is also that nowadays there's also experimental mode to run chemical parameterizations in the CCPP, not just physical parameterizations. So CCPP itself, the framework itself, is not part of the actual model code. It's more like a code generator, also referred to as a data broker, that relies on documented interfaces for both the host model and each of the physics schemes. So we refer to these as metadata tables. So at build time, the framework parses the tables and connects the variables by one of their attributes, the Ccp standard name. It then generates Fortran interfaces between the host model and the physics. And as this figure suggests, these interfaces can hook up the physics with the atmospheric driver in different ways. For example, in a traditional way where you'd call the physics right from the atmosphere driver, but also inside the dynamical core, which is known as fast or inline physics. These metadata tables, they are used together with inline oxygen documentation in the CCPP physics schemes to generate complete scientific documentation, as it's shown here in the screenshot. So the scientific documentation and the fact that each of the variables that a parameterization needs to be executed are described in full in those tables are one of the ways to accelerate the development of physical parameterizations. It's much less likely that you get units or something like that wrong, or dimensions. So how does CCPP know what files to generate and what schemes to call? It uses what we call suite definition files in XML format. These also get parsed at build time, and they're then turned into Fortran interfaces between the host model and the physics. So the suite definition file shown here for the operational GFS version 16 suite in the UFS contains a surprisingly large number of schemes for many of you, I guess, because of a fundamental difference between CCPP and other physics driver-based modeling systems. So all the glue code that resides inside these classical physics drivers and that connects the different parameterizations, and this is often tens of thousands of lines of code, they must be converted into what we call interstitial schemes. So some of the features of XML suite definition files are shown here. For example, the ability to assemble schemes in groups that can be called individually or all together, subcycling for calling schemes at higher frequency or with a smaller time step, and also user-defined ordering of the schemes. So one word of caution here, if users want to change the order of schemes, then they also need to make sure that some of the logic in the interstitial schemes works as intended, because some of it still depends on the order. So CCPP serves a dual purpose. On the one hand, it has to offer flexibility for research and development. And on the other hand, it has to provide the necessary performance for operational applications. So to achieve this, we came up with what we call multi-suite static build that allows you to compile multiple suites into one executable and then choose between them at runtime. And since there is no code branching inside any of these auto-generated suite caps, this code is pretty efficient computationally. Here's an example for the flexibility that we baked into that system. CCPP supports automatic unit conversions to expedite development and transition of innovation. So for example, here in FE3, cloud effective radii are stored in micrometer, whereas Thomson expects them in meters. The framework knows about the difference from parsing those metadata tables at build time, and then automatically injects the appropriate variable transformation into the auto-generated physics suite cap, as you can see here on the right. So there is a lot of exciting active development going on. One great example for successful community engagement is the recently added capability of building and running physics in the UFS in single precision. So this was a collaborative effort between the Navy, DTC, and NOAA EMC, and that was all spearheaded by John Michalakis' work on getting the single precision RAP-HER physics runs in the model, in the Neptune model going. So a bit more work is needed there, but we're on good track. Also, as Mariana already mentioned, the ESMF team recently contributed the exchange grid capability to the UFS, in which CMAPS was modified to act as a CCP host model and to perform atmosphere-ocean flux computations. And there was a typo that I just skipped over. All right, up until today, we had 5 releases of CCPP, each time with an updated and growing list of supported physics and 1 or more host models. From the very first version on, CCPP was released with the single column model that is developed by the DTC as well. And it's one of the key components of the UFS hierarchical system development. CCPP was also part of all the UFS medium range and short range weather app releases so far. And more are coming soon from Epic. In fact, CCPP version 6 will be released later this month and will support the UFS short range weather app release version 2. The CCPP physics library, the authoritative main branch, contains many parameterizations for the different categories shown here. And the color coding also shows you that this is a highly collaborative effort between multiple organizations and agencies. Universities as well. So with so many combinations to choose from, you need to make decisions which of these combinations, which is actually the suites, to support when you create any of these releases. So the approach we've taken so far was to support a small number, maybe only 1, 2, or 3 or so, of these vetted combinations of physical parameterizations for each of the UFS releases. And then a slightly larger number of suites for the parallel SCM single column model releases. So for the example of the upcoming CCPP version 6, we're going to support 4 suites with the UFS short range weather app. That's the operational GFS version 16, the rapid refresh forecast system version 1 beta, the Warn-On forecast, and the HER suite. And then 2 additional suites with the single column model. All right, changing gears a little bit. An important effort undertaken in the last year focused on those CCPP standard names. They are really one of the key aspects of the CCPP because they are used to communicate variables between a host model and the physics. So whenever possible, we try to use standard names provided by the CF convention. But for many of the variables, we had to come up with additional names. We had to create new names, and it was difficult because we didn't have any clear rules in the beginning, so we definitely saw this proliferation of often poorly constructed names coming up. So to address this issue, the DTC worked with NCAR and the community to put in place a set of rules for creating new names, and also to assemble a dictionary of current standard names that are in use. So this is not the only standard name effort that has been made in the past. But unfortunately, again, this set of standard names is not connected with any of the other efforts in the United States. For example, ESMF standard names, the Physics Constants Dictionary, the JEDI Yoda Data Convention. So all of these standards were defined independently, and I personally see this as a bit of a missed opportunity, and hopefully something can be done there to be more interchangeable. All right, over the last few years, there was a team that was assembled to discuss code management practices for CCPP physics. This team has participants from various institutions such as DTC, the NRL, NOAA, and NCAR. So the main topics here are to discuss how the future collaboration on CCPP should look like and how to come up with standards for that. So as you can see here, there are common interests like parameterizations for some processes. How do we engage with the broader community? What's the code repository structure, standardization of schemes, and so on and so forth. One interesting point, discussion point, was centered on the idea of having a single authoritative CCPP physics repository for all models. That's currently not the case. Right now, we have an authoritative CCPP physics repo for SCM, UFS, and Neptune that's managed by DTC. And we've got an NCAR repository for CCPP compliant physics that are shared among the WRF, EMPAS, and CM1 models. And there's a reference to Laura Fowler's talk that explains that in a bit more detail. So as most of you know, in 2019, NOAA and NCAR signed a memorandum of agreement to co-develop the CCPP framework as a single system to communicate between models and physics. And it was actually on one of Mariana's slides and last slides about this ongoing, this new project, this NSF-funded project as well. So the idea was to jointly define the requirements for the next generation framework and then converge to one single common framework with a superior and extended functionality. A few of these high-level items are listed here. So augmented metadata standard, automatic variable allocations, the ability to compare metadata to the actual Fortran code and improve build system and code generator, and then very important for this community, especially advancements for chemistry. So this work was delayed once due to other activities at both organizations taking higher priority. And then ultimately NCAR decided to conduct a review of the CIMA project, which itself includes CCPP. And this basically brought these efforts to a halt for now. So one of the efforts we were undertaking at this time was to develop a process for joint code management of the framework, very similar to those efforts for the CCPP physics. So back in those days, we had regular weekly meetings between NCAR and NOAA to discuss the design and future development of the framework and any issues that came up. This has basically stopped since the beginning of the year. There was very little activity going on there. So here's the original timeline for converging to a common CCPP framework for both sides. And as you can see, we decided to approach this really from two angles, with NCAR CTD starting to develop the next generation code generator called CapGen based on the joint requirements that we fleshed out after the MOA was signed. And then NOAA DTC incrementally adopting some of those new features and design specifications so that a future transition to CapGen in the UFS would be almost seamless with very little disruption for the users and developers. Of course, this is no longer valid. So it sounds a little sad probably, but there are also some good news for CCPP on the horizon as regarding the transition to operations at NOAA. So this is a schedule for when CCPP will become operational in the various NOAA models. It starts in 2023 with the hurricane analysis and forecast system and the rapid refresh forecast system, and then later in GFS and GEFS as well. So just basically to wrap things up, CCPP was created and implemented in the UFS and other modeling systems to facilitate the development and testing of innovations and to lower the bar for adding new physics or transferring them between the models. And while there is still some uncertainty on the future implementation of and development of CCPP at NCAR as part of CIMA, we're still hopeful that one day, not too far out, we'll see CESM and EMPAS shipped with the CCPP framework, the one CCPP framework under the hood, and that NCAR will join NOAA and the Navy and other organizations like NASA and DOE, where individual groups have already started to experiment with CCPP. So I have got a bit more time left, so let me quickly go to the additional material. What I didn't mention is that because CCPP consists of a code generator and it has a very flexible metadata standard that gives you a lot of information about the variables that need to handle, There's a ton of opportunities for development. So we are talking about things like automatic array transformations if the index ordering is not correct, vertical flipping, calculation of derived variables, potential temperature from temperature and geopotential. A visualization tool that shows you how a variable travels through a suite. Is it modified somewhere? Is it just read in, or is it bypassing a certain scheme entirely? That's actually already in progress. It's basically finished that project. Better error handling to include traceback information, being able to split to specify whether you want to have time split or process split schemes or groups of schemes in the suite definition file. Logic to handle schemes that update the state in place or return tendencies, extended diagnostic output capabilities, then improved handling of constituent arrays and properties, especially for chemistry, automated saving of physics scheme states for restarts. We've got more. There's also ideas about creating a generalized way to create either CCPP or NUOPSI caps for physics so that you can run them either inline or as a separate component. The ability to leverage GPUs by automatically offloading this code onto GPUs in the auto-generated caps. And then there's also some idea about how to decompose and recombine grid columns into different surface types for selected physics that have been floated around. So that's basically all I had to say. I'm going back to my summary slide. Thank you for your attention, and I'm looking forward to your questions either now or later on offline.
All right, thank you so much, Dom. So we definitely have time for some questions. I welcome you to raise your hand if you have that function, or put them on the chat. Let's see. I don't see any raised hands yet, but Adam Harrington has a comment on the chat. Adam, you want to unmute yourself and just speak your comment?
Yeah, I just wanted to voice some disappointment that the CCPP is stalled right now, pending the CEMA review. Can you say anything more about it?
I can tell you that I'm going to be on the CEMA review panel starting from next week. I think it is, or in 2 weeks' time. And then hopefully I'll be able to tell you more. I'd have to defer you to my dear colleague, Steve Goldhaber, who has maybe a little more information on that.
Mm-hmm. Okay,
Sorry.
thanks.
There is another question on the chat from Richard Loft. Richard, you want to unmute yourself and ask?
Sure. Can you hear me?
Yes.
Yes.
Yeah. Okay. Can you say something more about the timeline and strategy for GPU offload? It seemed like it was an opportunity for development, but assuming that the CEMA review goes through and CCPP continues at NCAR, I'm just curious what the thinking is about where it is in the priority list.
So we've had a project funded at NOAA GSL to prototype some of this work, and it's been partially implemented. We GPU-ized one of the schemes in CCPP, the Grell-Freitas convection scheme, and then sort of hard-coded the calls into the model, so we would bypass the framework for this, but just to demonstrate that, you know, there's a physics package in CCPP that can be called and run on GPU, and that has shown, you know, great potential in terms of speed up. With respect to when that work on the framework would start, my personal opinion is it's relatively high up in the priority list after the next GFS operational implementation. And Lisa, please correct me if I'm wrong, because I know that EMC is also looking into GPUs in the future.
Yeah, so
yeah. Could I just follow up real quick on that? Is that written up anywhere, that technique that you use to bypass or GPUize the Grell-Freitas?
There was a presentation, Lisa. Are we able to share that presentation?
Yeah, we should, yes.
Okay.
I'd appreciate getting access to that and looking it over just to understand what you did in more detail.
Okay.
And just to add, in terms of prioritization, for GPU offload or many of the other developments that Dom mentioned, we are hoping to conduct a CCPP visioning workshop in which we would discuss that. We don't have yet the funding for conducting that workshop, but we're still assembling funding, and if things work out, that would happen later 2022 or early 2023, and that would be a great venue for discussing in a multi-institutional setting what our priorities are and how to go forward to fund some of those priorities. So this the CEMA review is really important because if Steve Gohaber and colleagues already did a lot of development on this next generation CCPP framework, and some decisions need to be made about that going forward for NOAA or not, so that this development such as GPU can be done on top of the existing system or this next generation system. So we are going to be participating with a lot of interest in the CEMA review. And with that, I'm going to thank Dom for his presentation. If you have more questions for Dom, please save them to the final Q&A or put them on the chat. And we're going to move on with the presentation by Brian Dobbins about CESM and new technologies, clouds, containers, and accelerators, GPUs. So go ahead, Brian.
Everybody, yeah, I'm Brian Dobbins. I'm a software engineer in CGD. I've got a lot of material here, so I'm going to go pretty quick, but I'm happy to also have offline conversations about any of it. So to jump right in, I'm going to start with talking about CESM in the cloud. We've been doing runs in the cloud for a while now, but we finally have production science runs and production workshops. So we've really made a lot of progress lately. On the left, you see these production science runs. These are large. It's a 1 degree Wacom case, about 15 million CPU hours, going to generate about a petabyte of output. And the whole workflow from running to post-processing to archiving is all done on AWS. On the right, we recently used the same infrastructure to develop to deploy a Jupyter Hub to run a training for CTSM. There are about 60 plus users, automatically creates the counts, makes it nice and easy, multiple queues, node types. So these are really successful projects, and we're hoping to make these tools available to the community soon. So how do we use the cloud? You just need a cloud account and credentials. Then you got to learn the cloud interface. Then you got to choose a node type. Then you got to choose a network type. You got to choose a storage type, a storage size, a cloud region, create a YAML file, configure instance settings, configure network settings, launch cloud resources, update the OS and tools, install the libraries and compilers, install and configure CESM, and then you can do your science. Now, I've actually made this a little bit simpler than it is. I skipped a few things to get this all to fit here. And this is clearly not something that we want the user community to do because this is not sustainable for them. So our approach is we're creating an API that makes this a little bit simpler. And so the idea is you have a user with cloud credentials, they access this API, and it does all of those steps for you. So this offers several key advantages. It's a lot easier for scientists. We can support multiple clouds with the single interface. You don't need to learn 2 different cloud interfaces. And we can add features. So you can just click a button and select to add a Jupyter Hub. You can phone home. So we can, if you have trouble with a run and we want to support that, you can enable remote access via an encryption key from NCAR. Tools like the post-processing containers and stuff, we can all deploy that automatically for people. When I talk an API, that's a pretty abstract, idea. So just as an example, here are 2 interfaces that I've sort of played around with, but we don't have anything up and running for the public yet. On the left, you see a website. This is pretty easy. You select, what kind of cluster type. Here I did single users. So you don't see any account information. You just enter your access keys. You click the button, and in about 10 minutes, it'll give you a SSH address that you can connect to. And on the right, I'm running this verbose version, so it's showing you what it's doing. It's finding credentials, checking the mode, selecting the node type, and that will return to you a SSH command that you can use to connect to cloud resources. So the cloud is really easy. That's the upside, or we can make it very easy. That's the upside. But let's talk about one of the downsides, which is the cost. So right now with on-demand pricing, you see in the table above, prices have improved. They've gone from 11 cents an hour on the older generation of nodes to about 3 cents an hour. But the derecho cost equivalent with my back of the envelope calculation is about 0.3 cents an hour. So for compute, it's still more expensive to use the cloud. Now, another thing, and I've added this slide, there's a lot of talk about in-cloud data lately and cloud-based analysis. And one of the things that when we do HPC, we often think about compute costs and compute hours. We take it for granted that data transfer is free. In the cloud, that's not the case, and there's costs. So for example, if you had to store 20 terabyte in the cloud per month, that's not too bad. If you wanted to download that, you pay a decent chunk, and that's per download. So if somebody else downloads it again, you pay that again. So for example, we have this Arise data that we're hosting in the cloud, and if you were to download the whole thing, it's $30,000. If 10 people download it, that's $300,000. But thankfully, there are 3 ways of hosting data in the cloud. One is you get generous support from AWS and the Amazon Sustainable Data Initiative, and they will host it for free. They've done this with CSM Lens data and this Arise data. But otherwise, for data, you either have the host has to pay for it, which is a potentially unbounded cost, or the downloader pays. This is problematic for open science in the cloud. Okay, so move on really quickly to containers. We talked about the clouds offering configurable environments and the benefit of that, because we can pre-install things, and containers do the same, but on your own hardware. So this makes it really easy to provide ready-to-run tools to the community. So it greatly simplifies the ease of porting, and you can ensure some cross-system compatibility. Our biggest containers are our CSM and CSM lab containers. We've got a lot of use out of these. They're still sort of in a preview mode, but I got to update those soon into official releases. And the idea is we just have a base layer, which has common OS tools and libraries. So everything you need to have an environment that you can use, a Linux environment, even if you're running on Windows. Then on top of that, we can optionally add a Jupyter Lab. And I say optionally add a CESM version because we can have a release version, or if you're doing development work, you might want to clone your own repo. And so that way you don't need to have a built-in version. You just use the base container, and you still get a consistent environment and analysis platform across any users. Now, containers aren't limited to CESM itself. We're also containerizing a variety of our tools. So we have some CAM topology tools are recently containerized. The CSM time series generation tool. This is a big one that's gotten a lot of interest. And Allison Baker's going to talk later today about some compression tools. I've started working on a container of that. We can make these parts of workflows for people. So you don't need to install your own software. You can kind of just use the container and it's done for you. On desktops and laptops, this is typically used via Docker. And on HPC systems, we usually use Singularity, which has now been renamed as Aptainer. And if this is of interest to you and you don't know how to use this, because these are some new skills, learning to use Docker or learning to use Singularity, but you want to get in touch and we'll happily help you out with that. One of the benefits of these configurable environments, the cloud and container, is that you can unify them so that what you see on one is what you see on the other. And this is really helpful because it means that if you're a new user to CESM, you can learn on your own laptop. And then you can use the cloud, and moving there, transitioning to that is trivial because it's just it's the exact same environment. So you don't need to worry about any differences, different paths, different directories. It's all very easy. And on the topic of standardization, another thing we're working on is standardizing Jupyter environments. We call this EASE, the Earth Analysis Science Environment. And this is just a pre-installed Conda environment with the Pangeo and various CESM tools. The idea is we don't want students to have to go through Conda install and modifying their own environments. We want everything to sort of work out of the box. This is with our new diagnostics, various packages, and this will be updated on a rolling basis. At the end of the day, we want the same EASE kernel to be available on Derecho and Cheyenne and our cloud and container environment. So any NCAR environment would have the same kernels available, ready to use out of the box, no configuration necessary. Okay, so one of the biggest topics I think that people always wonder about is accelerators in CESM. And there are 4 key challenges here that I'm going to talk about. And the goal today is that this is actually a really complex topic, and it's often misrepresented as a pretty simple one. People show a performance number, they say, let's do this. And I'm going to try to just kind of get you to think about this in a more complex manner. So let's start with performance versus efficiency. So we don't have a GPU capable version of CESM. So as a proxy, I took MPAS Atmosphere version 6 at a 1 degree resolution, 58 vertical levels. This is the CAM7 vertical levels, double precision mode. And if I run it on the derecho hardware, so this is the GPUs, these are the derecho GPUs, and the CPUs are the derecho CPUs, you can see this impressive difference. I mean, so basically the GPU is about 2.75 times faster than the CPU. So roughly 3x on a single node. And that is impressive. This is more power efficient. It's a really big win. Now, this is not the whole story though. If we scale out this 1 degree run, well, then we get a different story. So the GPU needs a lot of parallelism to perform well. And so it rapidly runs out of that parallelism and it doesn't scale as well, whereas the CPU scales very well. So here we have GPUs are more efficient, but the CPUs are able to perform much better. Now, in this case, this is using an older version of MPAS Atmosphere that has a known issue with lacking GPU direct communication. So this will improve a little bit. But at the end of the day, for the 1 degree workhorse resolutions, there are still advantages to both. This is a great result from GPUs. There's really great value in the efficiency, and there's also great value in the speed of the CPU. So for example, paleo runs, you're going to definitely want a CPU for that. Another big question when we talk about this that is this issue of science capability versus capacity. This is something we talk about in HPC with systems. And it boils down to, should NCAR focus on enabling a few uniquely large scale runs or supporting a high volume of science at workhorse scales? There's not a right or wrong answer here. These are both great approaches, and I think we need input from the community. I'm a bit of a numbers guy, so I like to visualize things and have data. So I do a bit of an analysis here. So Cheyenne has 145,000 cores. That's 1.27 trillion core hours per year with no downtime. This is 24/365. About 55% of Cheyenne goes to CESM. That's about 700 billion core hours. And so if we do a B1850 coupled run at 1 degree, it takes 2198 core hours per year. Well, with nothing else being done at the system, no analysis, no higher resolution, no lower resolution, we get around 320,000 simulated years per year of Cheyenne. If we were to do a 3.75 kilometer run and we apply linear scaling to this, that's 32x in the lat long direction and 32x in the time step, we get about 9.7 simulated years per year. So with 55% of the system for one user, that would be less than 1 model year per month. So there's great science to be done at this resolution, but it's a question of what are we aiming for? Are we aiming for large scale runs, or are we aiming for a lot of runs of different science at workhorse resolutions? And this is where we need input from the community. On code portability, this was a concern for us that is no longer a huge one, thanks to some great work that CISL's been doing. So basically, a lot of the early work on accelerators was done with NVIDIA's OpenACC or OpenACC on NVIDIA GPUs. I'm sorry, that's my dog barking. We had concerns about OpenACC because we are a community model. We need portability. We can't tell people you have to run NVIDIA GPUs, and the Intel GPUs wouldn't support it. So now we were leaning towards OpenMP, and CISL's been working on both OpenACC and OpenMP, and they've been using this Intel converter and exploring that. And this is a great path forward for us because it enables us to look at embracing OpenACC early and having automatic conversion. So it's not a sunk cost on any development work we do. Finally, one of the biggest things, of course, is the people time. So models of similar complexity have taken around greater than 10 FTE years to GPUize. So do we focus our efforts on this or on science features or usability features? Again, open-ended question. There's value in both. And can we get additional funding or community help to do both of these? This is, that would be great. Finally, there's still relatively low adoption of GPUs in academic systems. If you look at the top 500 US academic sites, I think the CPU nodes to GPUs are around 20% of them, and a little less than that in an informal Exceed Campus Champion survey. Finally, I'm going to move very quickly to an extra slide I've added after this discussions on Monday. So one thing that, so Everett mentioned serving underserved communities and global use of CESM. And one challenge we're seeing now is that as our use increases via clouds and containers, it's coming from novel IPs, there's more users, and all that input data is being funneled through NCAR. Well, that doesn't need to be the case. We can put data in remote servers and have data go through there. Jim Edwards did some great work on enabling this in SEAM. So we just need to have the data hosted somewhere. We're talking to cloud vendors about that. Longer term, because of cloud egress charges, you really need some sort of mesh network which relies on the fast networks at university sites to pull in data from elsewhere. And this is something that we're beginning to think about and want to pursue as we move forward. So I know I moved very quickly from that through all this. Our summary is we have CESM and Jupyter Hub usable via AWS for science and training. It's pretty easy to use, but not as cost effective as on-prem systems. Containers are great. They enable ready to run applications. And we're looking at some new tools, like again, the time series one gets asked about a lot. So we'll try to make that available to people soon. And the big one, our GPU approach is a careful balance of technology, science, systems, and people to do what's best for the CESM community. The technology is very exciting, but we're trying to just be a little bit conservative in how we embrace it to see where it's really going to serve us best and balance those issues of resources with time and systems. Finally, data access, as I said, is a growing issue, and we're looking at some ideas here. So sorry, I went through that very fast, and I apologize for my dog barking. If you have any questions, I'm happy to take them, and thank you.
Yeah, thank you so much, Brian and Brian's dog for this talk. So if you have questions, please raise your hand or put them on the chat, and then we'll ask you to unmute and ask your question. I don't see any hands yet. So Brian, maybe you can talk a little bit more about this aspect of choosing what parts of the modeling system. Oh, I see Rich has a hand now. So Rich, go ahead and I'll ask my question later.
Okay. Yeah, I just wanted to make a comment about this that, you know, Brian, you and I have talked, and I think the best way to convey all this about GPUs is that GPUs are all about the data parallelism, and that can come from either the size of the ensemble or the amount of points available in the grid of the model, for example. So, you know, I think the issue with small ensembles, low resolution problems are not the GPU wheelhouse. So that's just to sort of follow up on that and flesh that out. Your question, back to you.
Oh no, please go ahead.
I was just going to ask you to talk a little bit more about, you know, how you're working to select which parts of the system to offload to GPU versus CPU. I imagine you're not testing, you know, entire system on GPUs.
Oh, I think that question in the chat was actually for Dom from the last talk. Yeah. I mean, so I think we have a talk coming up from Jian-Sun about some GPU microphysics, but you know, we're still sort of taking a large scale look and not working to massively convert things to GPU yet. We're kind of letting the technology simmer down a bit. Yeah.
Okay, I don't see any questions on chat. I see a comment from Eric. I did get kicked out for a couple minutes there, so if something happened, I don't see it. So at this time, I don't see any questions or any other hands raised. If someone wants to ask a question, please speak up. Okay, well, if not, let's just go ahead and move on to the next talk. We're going to continue on the topic of GPUs, and we're going to have Jian-Sun talk to us about enabling the execution of Pumas on GPUs. And Jian, we can see your screen. It is not in presentation mode yet. Yep, looks great, so please go ahead.
Okay, thank you, Alicia, and thank you, Brian, for giving a nice background introduction about GPU computation, which I think is very helpful for my talk as well. And good morning, everyone. I'm Jim from ANCA. Today, I'm going to present the work that I collaborated with John, Sherry, Brian, Andrew, and Kate during the past 2 years. The title of this presentation is Enabling the Execution of Pumas on GPUs. Here, Pumas refers to the cloud microphysics scheme used in CAM right now. And the presentation will be outlined in the following sections. First, I will describe briefly what is cloud microphysics. Then we will do a code overview of the Pumas code in CAM. Later, I will describe what is the methodology we use to offload the CPU Pumas code to GPU and some preliminary results. Finally, I will draw the conclusion and mention some future work. So what is cloud microphysics? Cloud microphysics usually refers to the small-scale processes that drives the formation and evolution of cloud and precipitation particles. Cloud microphysics is closely related to many atmospheric phenomena and disasters like hail, thunderstorm, and tornadoes. The figure on the right hand is borrowed from the paper published by Morrison in 2020, and it shows that in cloud microphysics, it contains more than 10 sub-processes, and the number could increase with our increased knowledge. Therefore, it is usually difficult to represent cloud microphysics accurately in a climate model, and we typically have to use a parameterization in this case. So in CAM, we use Pumas, which is short for parameterization of unified microphysics across scales. In the Pumas code, it contains about 4,900 lines of source code for the main calculations. It also requires some water vapor calculations from the CAM code that adds up additional 1,100 lines of code. Considering the fact that for the CAM physics code, it contains about 0.4 million lines of source code, Pumas only represents about 1.2% of the total CAM physics code, but it could contribute about 8% of the total computational time of CAM physics. Therefore, it motivates us to spend some efforts to optimize the code and seek some potential speed up. Well, we know that CAM is already highly scalable on CPU through MPI and OpenMP. Therefore, the strategy we use in our work to speed up Pumas is to offload it to GPU. Instead of working directly into the whole CAM code, we start from a caging kernel for Pumas, which is easy for us to do the code development, debug, and testing. In this particular work, we choose the directive-based GPU offload method to do the GPU porting. And in this case, we have explored both OpenCC and OpenMP offload directives method. The reason we use the directive-based program model is because it can keep a single source code for both CPU and GPU version of Pumas, which improves the maintainability of the source code. By using the directive-based method, we are basically adding pragmas to convert the CPU code to GPU codes. Therefore, the readability of the code is minorly affected. One thing I want to highlight, and I think Brian also mentioned in his talk, is that in this work, we use the Intel's auto migration tool to convert OpenACC directive to OpenMP offload directive, and it works very well in our case. So I put the link to that tool in this talk, and everyone who is interested in this tool, you are more than welcome to check it out and apply it in your production code. So by adding the GPU directive into the CPU code, we increase the source code lines by about 10%. We think is reasonable and also acceptable. Before I go on to show you some performance data, one thing I want to discuss is the correctness that I think is very important when we do GPU porting. So when we port the CPU code to GPU, usually we don't expect the results are bit for bit because we are running the code on a different platforms and we may have to use the different compilers as well. So the big question we ask ourselves during this work is, when we observe a difference, is this difference expected or is due to a code bug that we introduced during the code implementation? In this work, we use the CAM ensemble consistency test to examine the GPU code and ensure its correctness before we look at any performance data. So here's the first performance data from the caging kernels. In this plot, the black and gray lines are the CPU results on Xianyan and Casper from one CPU node with 36 MPI ranks. The purple and the red lines are for the GPU results coming from OpenACC and OpenMP offload method. Here, the GPU results only account the GPU computation, excluding the data movement from CPU and the GPU. The x-axis is the input data size, and the y-axis is the performance metric. With the higher number, the better performance is. Both x-axis and the y-axis are plotted in log scale. Here we can see that the GPU performance is consistently worse than the CPU ones, which is against our original expectation. Therefore, we want to do some profilings and looking for some potential reasons for this poor performance on GPU. So I will show some examples that we think is critical for the GPU performance. The first example I will show is some loop dependency in the original implementation. Here I give the example in the original Pumas code. So in this particular code, we can see that when we calculate the variable precipitation fractions, we have some virtual dependency for the K loop. Therefore, if we add GPU pragmas directly to these loops, we will end up with running both loops in serial on GPU because we have to run the outer loop in serial first. This really doesn't makes really sense on GPU because the column calculation is independent. Therefore, the solution for this case that we reverse the loop order, put the column loop at the outer one, and in this case, we can achieve some parallelism on GPU at least. Another example that we find is critical is that in the Pumas code, there is a very expensive calculation called sedimentations. And this sedimentations is repeated for different hydromedias in the CPU version of the code. And you can see that in the CPU version, the 5 sedimentation calculation is done in serial. But if we look at the implementation in details, they are actually independent from each other. So for CPU run, it's really not necessary to follow the same calculation workflow. Therefore, the solution we made is to add different stream ID to different GPU kernels for the sedimentation and run them concurrently on the GPU so that their computation can be overlapped and save some computational time. There are other optimization examples. I didn't list them all here, but after some optimizations, we can find the new performance data for the same caging kernel. So it's the similar plot than the previous slides, with the dashed line refers to the original performance data, and the solid lines refer to the improved performance data, or the performance with the optimized GPU code. First, we can see that although we have done a few GPU optimizations, the performance on the CPU is merely affected, which we think is really good. But for the GPU, the performance compared with the original one, the new performance on GPU is significantly improved. And in this case, we can see at a certain point, GPU is able to outperform CPU at a certain point, and when we increase the problem size, GPU shows more benefits. If we elect the two solid lines for OpenACC and OpenMP offload, we can see their performance is in general very competitive with each other. But in our cases, OpenACC is slightly better than OpenMP offload. Therefore, we will focus on the OpenACC results only in the next CAM evaluation. So in the previous slides, we have shown that we can benefit from GPU porting for Pumas in a caging kernel. The next question we ask ourselves is that whether we can maintain the same speed up in a real CAM production run. So in this particular case, we did a CAM simulation with the F2000 component set. We use the FV cycle at 1 degree and perform 1-day simulation. We are using one computer node for CPU results and only one NVIDIA V100 GPU for the GPU simulation. So here's a bar plot. On the x-axis, it's the data size that is offloaded to GPU per kernel launch, and the y-axis is the time per substep per MPI rank. So the lower number the y value is, the better performance it is. So first we look at the blue and the green bars that refers to the CPU results on Shenyan and Casper. We can see in our cases with different data size, the Casper result is consistently better than Shenyan, which is expected because Casper has a relative new CPU architecture. While looking at the GPU results, if we have the default value P column equal to 16, we can see the GPU performance is much worse than the CPU one because we spend most of time on the data movement between CPU and the GPU. However, if we increase the data size, reduce the data movement frequency between CPU and the GPU performance can be improved quickly. And at the end, we are able to achieve 2 to 3 times speed up compared with the best performance on CPU that is on Casper. Therefore, from this plot, we can see that the GPU-enabled Pumas can also outperform its CPU version, even if we are using it in a practical CAM simulation. If we focus on the GPU result, looking into the details of it and decompose the time contribution from different perspectives, we can see that for different P column values, the data movement time from CPU to GPU and the GPU back to CPU contribute much more than the computation on GPU itself. So from this pie chart, we can clearly see that the data transfer could be more time consuming than computation for the Pumas case. And that should be our next focus of optimizations in the future. So here is a short summary about what we have done. First of all, we have fully offloaded Pumas to GPU by exploring OpenACC and OpenMP offload technique. We evaluate the performance on CPU and GPU, and the result shows that even if we are using only one GPU per node, we can achieve some promising speed up compared with one CPU node. One thing I want to point out is that, in my opinion, OpenMP offload is relatively new compared with OpenACC. And in our work, we find that OpenACC still performs slightly better than OpenMP offload. Therefore, for people who are interested in OpenMP offload, as Brian mentioned in his talk as well, I probably will suggest more evaluation work to be done before you really use it in your production simulation. So that's what we have found so far. Talking about the next step, since we get encouraging results from one GPU per node, it is natural to think of using multiple GPUs per node and seeking potential speed up on GPU further. And in our result, we find that GPU favors large problem size. So in this case, we are interested at if the GPU speed up can be larger if we look at the high resolution CAM simulation that we probably have seen some results in the previous presentations as well. Also, we want to know that if our GPU speed up in CAM is sensitive to different Pumas configurations or not. And last but not least, we are preparing a manuscript to document in details about how we do the code porting and how we evaluate the results and how the scaling looks like between CPU and GPUs for different scenarios. So this work is funded by the NSF Earthwork Project and NCAR co-funding. Besides the co-authors listed in the presentation title, I also want to give a huge thanks to the contributions and the helps from different peoples, from different labs and organizations with their names listed in these slides. So with that, I would say thank you for attention, and I'm happy to take any questions.
Yep, thank you so much, Jian. So we definitely have time for some questions.
Sure.
So if you do, please raise your hand or enter your name or question on the chat, and we'll ask you to unmute. I do not see any questions yet. Yes, so Rich, please go ahead.
Yeah, Jensen, one thing I didn't catch was you talked about using asynchronous kernel launches in order to speed up the different microphysics.
Yes.
That's this stuff that you showed here, but how much did that actually speed up the code compared to with, like, if you turn that queuing off?
Yeah.
Just by itself. Do you know what I'm asking?
Yeah,
how big of an optimization jump did that provide on the GPU?
Yeah, I think in my impression, by using the async runs, it improved the Pumas caching kernel performance by like 10%. That's my experience.
Okay. So about 10%.
It's about 10%. And I would like to say this is really case by case, because by running GPUs asynchronously, we need to synchronize it at some point. And the synchronization is a very expensive operation on GPU computing. So it's really case by case choice, I would say.
Okay, thank you.
Thank you, Rich.
Okay, more questions? Please raise your hand or indicate that on the chat. Okay. Jiang, so have you been able to keep your code base like unified for, use in both GPU and CPU, or you have to keep separate codes?
So in this particular, thanks for this question, Risha. So let me go to my slides here. Okay, yeah. So as I mentioned, the method we use in this work is called directive-based parallel program model. And a nice feature of this method is that we can keep the single source code for both CPU and GPU, which means that we only have a single source code, but we can enable it on either CPU and GPU by some choice of compiler flags.
Okay.
Yeah. And thank you, Brian, for your encouraging comments.
Is this pretty much the only physics code that is being used in CAM, CESM, like using GPU, or is this one of a variety?
Yeah, thanks for this question as well. So to my knowledge, Pumas is currently the only one brought into CAM for a real GPU simulation. I know RTMGP, which is the radiation scheme, also have OpenACC and OpenMP offload directives, but I personally haven't tested so far. I think some people on the audience list, they might have experience, and hopefully someone can jump in and clarify it.
Yeah, I have my hand up to answer that question.
Okay.
Thanks, Rich.
Go ahead.
Yeah, I just thought if you look at the Jim Hurl's presentation from the Atmospheric Working Group yesterday, there's a status slide which shows the status of these things. There's a port, Jensen's right, there's an RTMGP version, which is being worked on by Brian Medeiros and company, getting that into the physics suite. And there's also work being done on Club under a DOE contract to GPUize it using offload directives. In that case, OpenMP offload directives. And all that's in this big table that's buried in Jim Hurl's talk from yesterday.
Okay, well, thank you. Yeah, that's a good reference. Well, I think that's it for questions. I don't see any other raised hands, so I think we are going to bring this first session to a closing, or the first half. So thank you to all the speakers so far. We're going to head into a break and reconvene at 10:25 for the second set of talks. But before we go there, let me ask Bill if there are any announcements or anything we need to know.
No, that sounds great. Great. We'll see you in 20 minutes. I guess I'll just remind people, if they joined a little late, that we would be happy to see you this evening at 5:15 at the Rayback Collective for those who are local and are able to join us for a little social gathering this evening. Thanks for a great set of talks for this first set. And thanks, Lisa, for moderating that.
All right, see you all at 10:25.
All right, Jesse, are you back? We'll get started in a minute or two.
Yeah, can you hear me?
Yes, good. Do you want to, if you want to go ahead and share your screen?
Yep.
Then we'll give people, we'll wait another minute or so to get started.
Sorry, just real quick. Do you see just the slideshow?
Yes, it
Okay,
looks good.
cool.
Yeah.
Awesome.
All right, I'll just say a couple quick things before we get started in the second half. First, for those who are just joining us for the second half, we'd like to invite you to join some members of the Software Engineering Working Group this evening at 5:15 at the Rayback Collective in Boulder, if you're local. So yeah, we hope to see a number of people there. And then just a reminder that, as in the other meetings, we're following the NCAR Code of Conduct here. So offering constructive feedback, sharing the air, acknowledging teamwork, encouraging innovation, showing appreciation, and considering new ideas. So with that said, yeah, I'd like to turn it over to Jesse Nussbaumer, who's going to be presenting on the Atmosphere Diagnostics Framework. So take it away, Jesse.
Great. Thanks, Bill. And thanks all for letting me speak. Real quick, there's an asterisk here because we found out everyone's been calling it the Atmosphere Diagnostics Framework. And then we found out 10 minutes ago that way back in original documentation was supposed to be the AMWG Diagnostics Framework. So but it's definitely the ADF. Anyways, I'm just going to talk about the package. And I first want to thank my collaborators, Cecile and Brian, who have kind of been with me at the beginning. They're the ones who even kind of started this whole project. Justin, who is a new associate scientist who's taking more and more of this work on, might eventually become kind of become his. And then Julie and Danny, who kind of also been contributing a lot to the development, and also that kind of like a lot of the thankless organizational work that we all need, but no one wants to do. And then Andrew Gettleman, I guess, for senior scientistness. So let's get started. Uh-oh, you gonna let me go for it? There we go. So, CAM, the AMP group has the AMWG diagnostics, which have been around. Actually, I looked at the common stuff, it's been around for over 20 years, and it basically provides push button diagnostics ability. Basically, you just send it the paths to your CAM history files, and it outputs a bunch of tables and plots, and it puts it all on a website. And it's still being used. I used it in grad school. People use it in the community. It's still being used for CAM7 development. And I want to give a shout out to it. I'll be amazed at the ADF last 20 years. And so I got to give credit to a software that can be around for that long and still being used regularly. In terms of the actual software itself, it's basically just a bunch of NCL scripts that are wrapped with a C shell wrapper. And so that's kind of where the issue is, right? So we have to move on. One of the reasons is because NCL is being deprecated. It's just no longer really supported by CISL. And although it's still can be used, eventually there will become a time where it'll just be really hard to maintain. The other issue is, in general, people have found it's relatively difficult to modify the AMWG diagnostics if you want to change, contours or levels or anything like that. And also, particularly, it's difficult to work with different vertical levels than what the original CAM was, which is a problem because a lot of the new versions of CAM have many different, we have a 58 layer and a 93 layer, and all of these, we need a diagnostics package that's agnostic to those differences. And then finally, which is, it's just because this package has been around so long, but it's lacking a lot of modern SE practices, right? It's not, there's no open development. It's not on a repo really of any kind. It doesn't have any sort of testing or CI systems or anything like that. So, given these issues, we realize we have to move on and build a new package to kind of deal with this. And so a lot of us in AMP got together and we discussed and we kind of looked through the community. One of the things with diagnostics, in my opinion, is in some ways kind of if not saturated, a very full area, right? There's a lot of packages. We looked at things like ESM File Tool, which is developed, I think, by DOE. We looked at MDTF, which is developed by NOAA, which all kind of do the same thing. And then during this, we built, myself, Brian, and Cecile developed in like 2 days, a quick Python thing, being like, this is what it might look like if we, started from scratch. And that's how we landed on. We landed on that straw man. So that straw man is now the ADF. And so, some ways that was great, but in other ways it did kind of immediately add a lot of technical debt. So if you were, those first 6 months when you saw it, you might have been like, ooh, that wasn't the best written code. And that was part of the reason why. And just real quick, there's the URL for folks who want to look at the repo. So what were the general design principles of the ADF? Mostly these design principles that I received from AMP, or the general kind of user group community that we're focusing on. One, which is again just like the old AMWG diagnostic, we don't push button capability, right? Basically, I just give you 1 or 2 inputs, like the paths to my model data and the paths to where I run all of the diagnostics written, and then I just literally like type go, and it just runs, right? And so then the ADF will generate all these process files, planetologies, regridded data sets. We'll generate tables with statistics, plots, and then finally try to put it all together in a website. And in the future, we might also see about putting it together on like a notebook or a book collection. One of the really strong things they wanted to be error tolerant. What this means, in this case is if I have missing, if I have analyses that require, say, the zonal wind field, but my model data is actually missing zonal wind, instead of just the ADF dying, it just says, oh, I can't find zonal wind, I'm just going to skip this particular analysis and try to move forward. So basically, the ADF will try its hardest to run to completion, even if it has to skip a lot. And of course, they'll print warnings, but even if it has to skip a lot, or even if it has to kind of bail on certain things. And this is because there's certain analyses which are much more expensive than the others, so we don't want to have to redo the expensive analysis that worked fine just because of another analysis downstream had a bug in it. The other thing that was really hammered to me was they wanted to be really easy to port. And this is actually almost the most important thing for the community. They cared about it more than like performance or even like code readability, things like that. Some ways this is not as big of a concern. As Brian Dobbins talked about the ease container, there's now systems that kind of solve this for you. But in general, at the time, we wanted to make sure that you could at least easily install everything you needed with Conda. The other thing, which is a little different, the ADF does a little different than other diagnostics, is we make a really concerted effort to use the minimal number of external Python packages, which we'll show later. Part of this is because even with containers, right, the less packages you have, I got to imagine, the easier it is to maintain over time. It also helps with development. Even during the development of the ADF, I ran into a dependency hell. And so, the more packages you have, the more likely that is. And so just trying to keep it to the necessary packages was kind of our goal. Even if that means we have to write some code in-house, it's fine then passing it off to a package that might not be around 5 years from now. And then, they also wanted to be relatively easy to modify. Some of this is just kind of basic modularization. And so, also we wanted to have inputs. As I mentioned earlier, the AMWG, you couldn't really change things like contour range or the color table. And so the ADF, now we have a YAML file that the user can modify. So in this case, PSL is at the sea level pressure. It's a variable from CAM. So basically this, in the YAML file, it's something like this. It tells the ADF, okay, if you have sea level pressure, we're gonna use the orange color map. We're gonna use this range. We also have the ability for some basic unit conversions, right? So it'll come in Pascals, convert it to hectopascals, things like that. Then finally, right, almost all the diagnostics now are moving to Python. So ADF is also Python. And these are actually all of the packages we're using. We chose them either because they have a very large community base, right? Like Xarray or Pandas, or they're developed by NCAR. So we know we have a direct kind of connection to the developers. That's the case with like GeoCat. The other two NCAR focused ones I don't have on here, which we're working on adding, is Intake ESM and Dask. So, but we're trying to, hopefully these packages will be maintained for a long time and play nice with each other. This is this is kind of a complicated diagram, but basically the main takeaway is like the top 2 files are the only files that the average user should modify. And even then, the only one that they would have to modify is this config file, which basically contains, the information, again, like paths and maybe some settings like, oh, I don't need tables, so just don't run tables, information like that. And then basically passes it to an object, which is in reality a bunch of objects that inherit from each other. And then that object kind of does sanity checking. It calculates a bunch of derived information and metadata that we need. And then it calls, essentially, we have a function call that calls a list of scripts. And this is where if you're developing, you can add your script in following a certain API, and then the ADF will just call it. All of these will basically maintain the one that kind of is in the ADF now, but it's maybe not necessary going forward is the time series generator. We just needed one at the time. But again, as Brian Dobbins pointed out, there's a time series container, and there's talk about eventually CESM outputting time series. But so we'll see. But the rest, calculating climatologies, regridding to your observational data sets, and then doing analysis and plotting, and then putting it all on a website. Basically kind of the workflow of the ADF. So in terms of the, that does not look so great on my monitor, looks better in my terminal. Anyways, so the API, so if I have a script, analysis script, like my script.py, how would I bring that into the ADF? Well, all you have to do is at the top, you have to add a function header, and the function has to be the same name as your script. So my script.py has to be defined as my script. And then the only thing you have to bring in is the ADF object itself. The idea being that that ADF object will contain all of the data you need to run your analysis. And so we're developed basically a lot of different kind of get functions or methods to try to grab, are we comparing against obs or a baseline? What are the name of the model run cases? And then we also have even functionalities if you want to add your own config option to that YAML file. There's just a quick way to read it in. Right now, it's still one of the downsides at the moment is it still means that each independent script has to open its own files all the time. So we're hoping things like that will be lessened as we bring in intake ESM. So individual scripts don't have to do their own querying and reading and those sorts of issues. I'm going to skip this because it's going to be a live demo, and live demos, of course, are notoriously successful all the time. So I figured save it to the end. So I'll come back to that. So real quick, in terms of the current status and issues, and I feel like I'm flying through this relatively fast. So we actually hope to have version 1, which is kind of like having the base functionality of the original MWG diagnostics, ready by the end of the summer, maybe early fall. There's two things that are holding us back. One is we're actually just lacking observational data sets. This is kind of something that we have to pass on to the science community and be like, hey, what data set do you want to compare, the cloud variables against or the radiation against? We're also still missing, I'll show a lot of the kind of basic plot types, but there's still certain plot types we're missing, like time series or radial overturning, things like that. We have to try to move this forward, we have a weekly hackathon to try to address these issues. So, scientists are involved in trying to add these plots and try to flesh out the ADF. And if you want to join, feel free. We're happy to take any help we can get. One of the downsides also is currently works with monthly output. This is an issue, there's a lot of diagnostics like the MGO or looking at diurnal cycles where you need higher frequency output. And again, we're hoping that intake ESM will help with that. Another issue is ADF right now. It works fine with kind of standard, model runs, even to like maybe half a degree. But when you get to really long time periods, thousands of years, or really high resolution, it currently struggles. And so we need to improve performance, particularly via DASC. And then one thing is personally, I got caught in the, faster, better, cheaper conundrum. So I've had to kind of put a lot of the good software engineering practices like unit testing on the back burner, which means we have relatively low code coverage. And so, going forward, we kind of want to fix a lot of these, right? Implement intake ESM to allow for easier, a simpler API with scripts, and then also to manage sub-monthly data. I'm going to bring in DASC to, particularly for memory. I should back up, the constraint for these high resolution data sets isn't actually the CP, isn't the flops, it's the memory. It's just hard to load that much data into memory using a lot of the, kind of off the shelf stuff. So we have to figure out a way to distribute it. Obviously bring in additional plots. And also, as you'll see, the website can use some beautification, can get subjective. We also want to develop notebook interfaces especially on the front end, right? Because notebooks are great at kind of being a tutorial for things. So it's great at the front end to help explain how to run through the ADF. But then also at some point, it'd be nice to have it at the back end. So you can, whenever you're running through the ADF and then outputs a notebook, you can run again so you can share if you have a really specific diagnostic. And then finally, increase unit testing and code coverage. And the other thing, which I want to give a shout out to the community, is, in like model development world, we seem to have really good, robust regression testing and integration testing, right? There's hundreds of regression tests, I think, I'm sure for CESM. But for diagnostics, that doesn't seem to be as common. And in particular, there's a lot of concerns about like, well, how do you determine if a plot, which ends up being like a PNG file, is different than a previous PNG file? So it'd be great to kind of spread that out to the wider community and figure out what would be a good integration and regression testing for diagnostics themselves, particularly when we make small changes that shouldn't change answers. Okay, so actually, I'm going to exit full screen, and I'm going to show the website real quick. We got time. Well, you're just going to see it like this. So here's the website. As you can see, it's pretty basic right now, but you can tell all the different kinds of information we have. So you have tables. So you click on tables. It gives you for each run simulation. This is a case versus a case, so a cam run versus a cam run. So I can select on one. It gives you a whole lot of information for each variable. I also have comparisons, right? So I can say like what's the difference between the two cases over on the right-hand side and what the units are. Then we have different plot types, so like lat long. Here's cloud, low cloud. So you go, okay, I get the plots for low cloud. If it doesn't fit on your screen super well, like this one, I'm kind of getting to cut off the edge. You can just click it, and then you get the full thing, and you can download it if you just want that plot. We have vector plots. We have zonal plots, both as kind of just two-dimensional time series. And then also, if you have a three-dimensional variable, which I'm actually not sure if this one has. Oh, yeah, well, geopotential height's not particularly interesting, but right, you can also then get height latitude plots. And then finally, we also have polar plots at the moment to plot, precipitation over Antarctica or Greenland, those things. Anyway, so yeah, I'll stop sharing. I think right at like 15 minutes. Actually, I'm a little over. So, but yeah, thanks for listening. Let me get my Zoom back. And yeah, I'm happy to take any questions. Thank you.
Great, thanks so much for that, Jesse. Yeah, we do have a few minutes for questions, so feel free to raise your hand or put a question in the chat. Let's see. I think I first saw a question from Jim Edwards in the chat. Jim, do you want to unmute and ask your question?
Sure. I'm just wondering about the status of this working with the non-regular grids like SE and MPass and regionally refined grids.
Yeah. So right now we're waiting on. So GeoCat's developing that UX array system, which is designed to manage that. So until that comes online, yeah, we do. Right now, you have to regrid to a regular lat long grid. So, but hopefully, when that comes up, we'll be able to use non-regular grids directly.
Mariana, I saw you have a hand raised.
Sorry, I think that. So Jesse, this looks great. I'm wondering, where do you see the future, like say for when we release CSM3, as integrating this into the total workflow of a seam run? Not even for CSM, but as we move forward, it would be great to start integrating diagnostics routinely so that you spit them out as part of the run. And we're not doing that. So what's your vision for that?
Yeah, that was part of our original. I guess I didn't actually have it in the original design principle thing, but that was one of our goals. Yeah, and so it should be, assuming the environment has the Python modules you need. Yeah, it's literally just modifying a YAML file and then running. It's literally running a script, so it can be put as a job in a schedule or just run like that. And then also we haven't. This could be a discussion with Seam or whoever. It is. You don't have to actually use a YAML file per se. We could, you can just bring in the object and then add the information directly in Python. So, but yeah, it's designed to just be, it could certainly be run as a a compute job. And there's a few things we still want to enable some ability for a user to have like environment variables that then are automatically read in, like shell variables. But once that's get in, yeah, the answer is yes. Sorry, that was a long way of saying yes.
Rich Loft, I see you have a question in the chat. Do you want to ask your question?
No, actually, it got answered. Basically, it's around the same question that Jim Edwards asked about connecting with unstructured grids and with the effort that RIGEN represents to introduce, unstructured X-array objects for parallel processing. So I'm good.
Okay. Yeah, we're hoping to use that once they say it's good to go.
Let's take one more question from Brian Dobbins, and then I see there's a couple other questions, but we're going to have to move on after that, and either could have some discussion in the chat, or there will be time at 11:30 for some further discussion where this could be addressed more. So Brian, do you want to go ahead?
Yeah, I mean, I think this ties into the same workflow questions that Mariana was asking about. And this is just, you had this workflow of generating the diagnostics, and also it seemed like there was some automation for generating the intake ESM catalog. And I was just curious what the thinking was there in terms of where that sits. Should this be part of a diagnostics run or part of the whole workflow? But if we're moving towards making the diagnostics part of the workflow, maybe that answers that. That's sort of what I was thinking.
Yeah, I mean, we haven't fully decided this in the ADF side yet, but so we might have it as like an option. Like you can either have it generate an intake ESM catalog or not if you don't want it for some reason. But it's just I know a lot of other diagnostics, like in the ocean group and I think to the land group to less. I'm not as familiar with that, but they have a lot of diagnostics that expect a catalog, and so by having a catalog generated at some point in the workflow, it would help interface with those. I think that's one of the major motivators.
All right. Well, thanks again, Jesse, for that overview. Our last two talks for the morning are both on the topic of lossy compression. So the first one will be from Allison Baker on fine-tuning evaluation metrics for lossy compression of CESM data. Allison, okay, great. I see your screen.
That good?
Yeah. Great.
Okay, so, oh, sorry. Can I go?
Yeah, go ahead, sorry.
Okay, so as Bill just said, this is part one of 2 talks and on lossy compression, and this is work that I've been doing primarily with Dorrit Hammerling and Alex Pinard. Alex will be giving the next talk, as well as Haiying Xu, and many other people have contributed to this effort over the years. So as we all know, computers are getting faster, and thanks to the work that a lot of people, just randomly changing slides, a lot of people in this group have done, we can generate data at a crazy fast rate. This plot is data I got from Dave Hart. It's 4 years of data for our Glade usage and campaign store. You can see the green line is the campaign storage. Right now, the capacity is 92 petabytes. We're about 60% full. You can see that it's growing pretty much linearly. The current sizzle plan is that once the capacity is increased to between 100 and 120 petabytes, that will be it. So we will run out of storage. This is not a good thing. It will negatively impact science, and that is why it's been really important to us to look at lossy compression as a way to mitigate the problem. So for those of you that aren't that familiar with compression, there's basically 2 different types. One is lossless compression. This means that when we compress the data and then we reconstruct it, we end up with the same information we started with. So this is what gzip does. This is what netcdf zlib deflate does. The other type of compression is lossy compression. And as the name implies, we lose some information. What we started with and what we get after reconstruction are not exactly the same. And so the reason we need to look at lossy compression is that unfortunately, lossless compression is not that effective on data that comes from numerical simulations. This isn't particular to CSM, but it's just a general statement that's true. This is because on this numerical data, if you look, I'll put the temperature with, what would be in 64-bit precision. There's a lot of numbers there that probably don't mean anything at the end and are essentially random. And it's very hard to compress random data. In fact, for CSM CAM data, at most we get a 2x reduction, and usually it's a bit less than that. So we need to use lossy compression if we want more substantial data reduction. But the issue then is that we have to be careful about what information we're losing. Hopefully we lose the information that was random noise and didn't matter in the first place. So the goal in our work overall has been, we want to reduce storage, but we don't want to negatively impact our science. So we've been working on looking at lossy compression and CSM data for several years. And I just wanted to kind of go over some of the challenges that we face. I mean, the first one is, understandably, scientists are reluctant to lose any information that might be important. So we've really kind of tried to have this mantra of doing no harm and trying to figure out how best to evaluate the information loss for climate data. Lossy compression has obviously been around for a long time and is really popular in things like, video and images. But in a lot of applications, if the image still looks okay, if your movie still looks okay, you don't really care what was lost. But that's not true with scientific data. So we have to be careful. The variables have different characteristics. There's spatial and temporal dependencies. And just overall, the focus of our work has been kind of one, and this is what I'll be talking about in Alex as well, understanding the effect of lossy compression, developing the right kinds of tools to do that. And from there, going on to figure out, what are the quantifiable metrics that make sense for CSM and how can we use them to predict what optimal compression will be. And that's what I'll be talking about for the rest of the time, and Alex will be talking about. So the first thing we did in this journey was to establish feasibility that, it wasn't a horrible idea to use lossy compression on climate data. And we did that by thinking of ensemble-based metrics. And the idea was that, at minimum, we wouldn't want any compression-induced differences to exceed the ensemble variability. And this is sort of the standard we think of when porting to other machines and stuff. So it turns out this is very feasible with compression, and in fact is probably too lenient. The next thing we did was give scientists access to some of this data that we had applied lossy compression to. And this was an experiment, a merit that we jokingly called the Pepsi challenge. That's, if you're old enough, you'll know the reference up there in the upper right. And the idea was letting scientists look at the data and see if they could tell the difference between which had been compressed and not compressed. This data is still out there. 2 of the Lens 1 runs have been compressed, and it's very difficult to notice using standard analysis tools. But of course, if you want to be clever, you can figure it out, which are compressed and which aren't. But the question is, does that matter? And so we come to, okay, we really need to be looking at compression at these fine spatial and temporal scales. And doing this kind of analysis is really important. And simple metrics like, the root mean square error, which maybe is enough if you're just looking at an image on your phone or something, isn't enough for climate, where, for example, on the right, I have pictures of looking at the effect on the contrast variance of different compressors. So these are the kinds of things that we need to look at. Okay, so spatial temporal analysis tools. So basically the idea was that we need to be looking at things that emulate what climate scientists are looking at. So we need to care about gradients in space and time. We need to care about derived quantities like the climate relevant budgets. We need to care about changes in variability over space and time. So to look at all this, Alex and I and Anderson and Dorrit have been developing this Python package called LDCPy. And what it does is it helps you compare data sets in climate science. We're using it to compare compressed and uncompressed data, but you could compare any data sets that you want that are different for different reasons. And this has been built on the Pangeo software ecosystem. So it's using Dask and Xarray, and you can interact through Jupyter notebooks. And we'd be happy for other people to use it. We take requests. Alex and I have been using it extensively for ourselves, and he'll be mentioning it further in his talk. So we can look at all these plots and images and different things in an interactive way. But at the end of the day, if we want to automate the procedure, we have to be able to determine a few quantifiable metrics that we can use and some accompanying thresholds that we can feed in to tell us what levels of compression are optimal. So we've been working on developing a suite of metrics, and I have some of them listed in this blue box here. And those are things like, correlation coefficients that are good at noticing outliers, the KS test, which notices changes in distribution, relative errors. And then visual similarity is one thing that we focused on. It's quite critical for post-processing analysis. I mean, we just saw Jesse's talk where, looking at these different plots is quite important and often the first interaction with the data. So a visual similarity metric is basically a metric that tells whether or how, to what degree two images are alike. And so we actually had over 100 participants in an evaluation study a few years ago where we let people say, can you see a difference or not between this data? And from that, we determined that this structural similarity index measure was very useful, and along with a corresponding threshold. And actually, Jesse, I think this is something that would be interesting for you to use in regression tests for determining differences in your images. But anyway, I'll stay on track here. So from there, we developed this data structural similarity index, which was just a variant so that we could apply it directly to the floating point data. The reason we wanted to do this is we want to avoid generating the images at all, because we're trying to automate compression selection, and we may be looking at hundreds of thousands of time steps, and we cannot be generating plots for each time sets because that's way too expensive. And we also don't want our measurement to be dependent on plot specific choices. We just want more of a general idea of how similar images are. So this has been really useful for us. And in fact, it's kind of our primary metric we've been using. Here's a picture of just the surface temperature. These are using two different compressors, and they've reduced the data by the same amount. And the image on the right is a much higher quality. It's hard to see at this resolution, but if you zoom in, maybe you can see that there's some blocking artifacts that the compressor on the left has left, and we don't want those. And it's nice that the DSSIM picks this up well from the data, not even from the image, just from the data. So this bottom plot then, I don't expect you to be able to read the variable names at the bottom, but these are all the daily variables from the CSM1 lens data set. And the reason I have this here is just to basically show you that for a fixed quality parameter like the DSSIM, different variables are more compressible than others. So the height of the bar shows the amount of compression for each variable, and the colors are just different thresholds. But basically, you can see that some of the bars are quite higher than others, meaning some variables for the same fixed quality can get much more compression. Here's a plot that I think is useful to understand how these metrics work. So I have 5 different variables. They're in each color. And we've used this ZFP compressor. As we look at the plot from right to left, the solid lines indicate the file size. They're going down in a linear fashion. So as we're increasing the amount of compression, we're decreasing the file size. Now we look at the corresponding dotted lines. And when you go from right to left, here you see that initially the compression does not affect the quality at all, because getting a 1 means that we haven't changed the quality of the plot. But notice that these DSSIM dash values are not linear. So at some point they just drop off and the quality quickly degrades. So when you think about getting optimal compression and with these compressors and using a metric, you think, I want to stop compressing right before the quality drops off. So that's basically what we're trying to do. So there's 3 compressors that we're looking at actively at the moment. And our main criteria is that we needed to work with NetCDF data, obviously, because that's what our output data is in right now. And this has been pretty hard until recently, because most of the off-the-shelf compressors did not support NetCDF data. We had to pull out the data, compress it, stick it back into the NetCDF file. But now in the last year, the 2 leading DOE compressors, ZFP and SC, both have registered HDF5 filters that allow us to do compression through NetCDF4. That has been a huge for us as far as being able to use it and having others use it easily. Another method I'll mention is Charlie Zender's bit grooming algorithm. This approach is quite nice. It's basically a pre-filter. It's available through the NCO tools. It's easy to use. It's easy to understand. It's available now. And it's been quite successful when we've tried it out. So here's an idea of what kind of compression you could get for CAM data. For example, this is all with ZFP, and I've categorized the thresholds I've used as conservative, middle ground, and aggressive. And we have the compression ratio. So for example, the variable on the left, FLUT, if you look at the orange bar, it goes up to about a 6. This means that for the amount of compression that I've termed aggressive, I can reduce the file size 6 times more than the lossless compressed file. So this means it's about a 12x reduction over the original file and about 6 over the reduction over the lossless file. So again, you can see that the different variables react differently to the same quality metrics. And I would say that, even though I've labeled this aggressive, it's not really that aggressive in the grand scheme of things. And I think it would be very realistic to expect these kinds of compression rates from lossy compression. I'll just quickly, the variables I showed on the last page are from this CAM test set that we've been looking at extensively. This is available on Glade if you want to look at it. Let me know. We're always looking for scientists' feedback. And thus far, we've primarily worked with CAM data because it's been much easier. But now that we can use lossy compression via NetCDF, we're making it easier to look at other component model data as well. I've recently got input from the CLM and CIS groups on what variables they would like to look at in depth. And our goal is soon, hopefully, to compress the entire CSM1 data set with lossy compression and maybe redo some of the analyses that scientists have already done and see if we can see a difference. So this slide is basically what Alex is going to talk about, but I want to give some motivation for it. And that is, now I've shown you there's all these different compressors. There's all these different parameter choices, all the variables act differently, and it frankly seems kind of overwhelming to think of using this in practice. So clearly what's needed for this to be practical is some kind of tool to automatically select, for a given variable and temporal output and grid size to automatically select the right amount of compression. And this is what Alex will be talking about. So I think I pretty much covered all these lessons learned, and I'm not going to go on them here, but, working closely with scientists is important. We're always looking for feedback, and I just want to end with this thought that my hope is that applying lossy compression is going to be something that's not suspicious and scary, but it's just going to be something that you do when running the model, like you would choose your grid resolution and output frequency and precision. It's just going to be another thing that you do. And that's all I have. So if you have questions, just don't ask me about the optimal compression level, because that's the entire next talk. So.
All right, thanks a lot, Allison. I do see one question in the chat and from Kevin Rader. And so why don't we take that as we transition, and then maybe we can take some more questions on lossy compression after Alex's related talk. But Kevin asks, do these compression tools handle variables that use special values or masking values to denote an absence of data at some points?
Yes, they do. Now that you can use them. So before, that was something that Hying and I had to figure out how to handle ourselves, because we had to pull the data out of NetCDF and compress it and then basically stuff it back in. But now that these tools are available with HDF5 filters or Charlie Zenders just through NCO tools, all that is automatically taken care of. So it's really huge. And that was why we had started with CAM, because it has less missing values and things like that. But this is really a big development, and it's going to make it easier for everyone to use these methods.
Great. So yeah, so in the interest of time, let's move on again. Well, yeah, I think we could take some more questions for Allison after Alex's talk, if people have them. But let's transition to Alex Pinard, who will be giving another talk on lossy compression, predicting optimal lossy compression settings for CESM lens data, as Allison just introduced. So Alex, are you able to share your screen?
I can share my screen now.
All right.
All right, is that visible?
Yep, that looks great. All right, go ahead.
Great. All right, so yeah, today I'm going to be talking about sort of our process for predicting optimal lossy compression settings for CESM lens data. So my name is Alex. I'm a PhD candidate in statistics at the Colorado School of Mines. Allison, who you just heard talk, is my collaborator at NCAR, and Tolerant Hammerling is my research advisor. So currently, to obtain these sort of compression ratios like Allison showed in our previous presentation, we're taking a sort of brute force approach to figure out what the optimal compression settings are, meaning we're trying every combination of compression algorithm and parameter setting that we have available to us, and running a suite of metrics on all of that compressed data to sort of figure out which one can pass all these metrics and yet still give us a high compression ratio. And it's very computationally intensive. So what we want is a model that we can use to predict this compression level in a way that's a lot more computationally efficient. And so to do that, we're trying to model this as a classification problem. In a classification problem, sort of to review, we have data sets, some data that we're using as input to this model, and corresponding labels, which are, in this case, our compression settings that we're trying to match with them. And that figure on the right sort of illustrates what I'm talking about. We'll see it again. So the output classes that we are looking at here are like I said, the compression the compression algorithm we want to use, which can include either ZFP, big grooming, or SZ at this stage. And for each of those, there's a slightly different parameter that or compression level, I guess, that we're trying to tune. So for ZFP, it's the level of precision. For bit grooming, it's the number of significant digits of the original data we're trying to maintain. And for SC, we have an absolute error tolerance that we can specify. And these parameters are the output classes of our model. And we select a series of possible levels that cover the range of likely optimal compression settings for all of our variables. And as Allison briefly mentioned, we're using these 4 metrics to determine if a data set has been optimally compressed. So that includes the data SSIM, Pearson correlation coefficient, Kolmogorov-Smirnov p-value, and spatial relative error. We, as input to this model, we have the first 2 years of CESM large ensemble CAM variables in daily output, which is about 47 different variables and 730 time steps for each variable. So we have several thousand data points to work with. And so, as I mentioned, currently we're taking a sort of brute force approach to finding what the optimal compression level is. And I was going to go into just a little more detail to show exactly what that means. So on the right, this figure here is a plot of, so for each column of this plot represents a single variable. And then as we go down the plot, we are increasing the data SSIM, which is the visual similarity of the data set that we're working with. So as we cross each of these thresholds, the aggressive threshold, that means our data is considered similar under the aggressive DSSIM threshold, which is 0.95. And at that point, we use the very next compression data set. So in this case, for LHFLX, we're looking at ZFP-P12, and that's our optimal compression level according to the data SSIM. And as we go on, we also find optimal compression levels using different thresholds for the DSSIM, so middle ground and conservative thresholds. And this is sort of also generic for each of our thresholds. We sort of repeat this process also for the correlation coefficient, spatial relative error, and Kolmogorov-Smirnov test. And we repeat this for every variable to come up, and every time slice to come up with the ideal compression settings for a single variable. And we end up taking the most compressed variable that passes those metrics. So now that we have an idea of what an optimally compressed data set is supposed to look like, we can tackle the problem of finding a computationally feasible statistical model for this problem. So this requires selection of features from these data sets. We're sort of going to extract these features from the data sets and use them as input to the model. And we extract these from the uncompressed data sets because we don't want to have to compress at several different levels. That sort of defeats the whole point. And selection of appropriate models and model setups for this type of classification problem. So there are a lot of existing classical statistical models that we can apply to this sort of problem. So we have random forest and boosting models, which are sort of shown on the right here. They are sort of a branching tree that starts at the top and works its way down, that applies some rule to the input features and ends up, as we go down to the very end leaves of the tree, giving us a label for what our data set optimal compression level or compression algorithm will be. There's also a few others. So there's support vector machines, linear discriminant analysis, deep learning, and aggregate models that sort of look at the results of several other models to come to their conclusions by taking the mode, compression level, or something like that. And we have also other models, such as convolutional neural networks, that are sort of implicit feature models that discover the features on their own. So the explicit feature models require us to come up with features for our data, which are used directly by the model to infer a label. So far, for this sort of crude first pass at creating these models, we've come up with 8 different features that are somewhat useful in helping us predict the optimal compression level. So those include the mean, the variance, the north-south contrast variance, east-west burst differences, number of zeros, range, median, probability of positive value. So some measures of centrality of the data, some measures of variance, some measures of the size of the data, and a couple of others. To collect all these features, as Allison mentioned, we're using this LDCPy software package that we've developed, which is sort of designed to do this comparison between two different data sets. In particular, we sort of designed it with compression in mind, but it's not specific to that use case. And it allows us to perform all of this analysis to generate these features. And to compare differences between the data sets, and also allows us to do things like plot the data to sort of give us a better sense of how the data, the original data, compares to the compressed data. And Allison said, I developed this along with Allison and Anderson, and Dorit has been really helpful in providing guidance for this package as well. To each of these models, we run a parameter sweep over several possible values for the model parameters, which vary depending on what particular model you're looking at. We train each model under each set of parameters, and using our validation data, we can sort of come up with an idea of what parameters for that specific model are performing the best. And once we have, once we know the ideal parameters for each model, we can test each of our models using this left out set of testing data, which includes 8 different variables that have different features from the original training data. And we don't have great results yet, mostly because our features that we've chosen, as I said, are sort of crude and don't quite give us perfect separation between each of the classes that we're trying to predict. But we expect that as we try our convolutional approach, we might come up with some more features. So the sort of challenge here is to find features that hold generically across these data sets. So they may look entirely different. In this case, these two data sets are optimally compressed using the exact same compression settings, but it's hard to tell just visually what it is about these two data sets that are making them optimally compressed using the exact same settings. And so for that, we are going to try a convolutional approach. So as I said, the explicit feature models are simple and fast and easy to interpret, but we need to find better features that we can feed into these models. And the nice part about a convolutional network is that it sort of discovers features on its own through the process of training the network. And we can use those new features to feed back into the explicit models to improve those models. And a sort of a quick review of the convolutional neural network approach. So we have some input data set. In this case, we're inputting the entire, we could potentially input the entire data set at a single time slice. We convolve that using a series of filters or kernels to come up with intermediate levels, which are called feature maps, which can represent different aspects of the image. So you might have a kernel that selects for edges in the image, like horizontal, vertical, diagonal edges. You might have kernels that sort of smooth the image, and whatever features arise can be sort of seen in these feature maps, which these feature maps are then condensed to sort of summarize the overall presence of the features in a region of the map. And that process is repeated. And at the end, we use the generated features in a dense neural net, like normal, to predict the optimal compression level of settings. So at this stage, the model is not very sophisticated. We're subsampling these images by 36 times to reduce the time to fit the model. We're using the image data directly, and as I showed before, if our data looks completely different, it's not surprising that the CNN can't pick up on features of the data that are maybe not visible from just looking at the raw data. We're also modeling only one step of this process. So we're only modeling either selection of the optimal compression algorithm or the optimal compression parameters conditional on a single algorithm. We're using a single hidden convolutional layer and a small collection of CES and daily variables, and we're not including any of the explicit features. This is all very work in progress that we've sort of just started in the last couple of weeks. So no great results, as I said, but we definitely have a path forward. Looking at how this model is coming up with features, though, as I said, may give us insight into how we can improve the explicit feature models later on. So the end goal here for the convolutional net is to have a sort of two-stage model where we have one model that first selects for the optimal compression algorithm, be it SCZFP or bit grooming. And then conditional on that, we have a separate model, which may or may not be a convolutional neural net that selects for the actual optimal parameters within that, given that compression algorithm. We'll be using some interpretable techniques such as saliency maps to investigate and improve the other models, or we may end up finding that the CNN approach itself is the most ideal approach. We're not really sure yet. And we're also going to try pre-processing the input data. So instead of maybe looking at the raw input data, we might look at something like the gradient fields of the input data as our input. And a quick summary, so sort of how this relates to CESM. We're hoping to make this sort of an automatic process that happens whenever you run a simulation. So there's just one automatically generated configuration file, like a YAML or a JSON, that supplies the compression settings. And it'll have some preset default settings, and it only really needs to be edited if space or accuracy of the data are of special importance. Otherwise, the user doesn't really need to do anything special. The compression will just run and sort of under the hood, and nothing else needs to be done. And that's all I have. So thanks for listening.
All right. Thanks very much for that. Great talk, Alex. And I do see one question already in the chat from Brian Dobbins. Brian, do you want to ask your question?
Yeah, I was just curious, basically, if you've looked at higher resolution runs and how compression rate and performance changes, and also if there is a sort of rule of thumb, if if it does it in chunks, which is sort of my naive understanding of how these things work, can it be parallelized? And just speaking more to the performance issues of how to do this effectively.
Do you want me to answer that?
You can answer that, yeah.
Yeah, so it really depends, Brian. It depends on the compressor. Some of them, like the ZFP compressor that I showed results for, it's a transform compressor. It's quite sensitive to the chunking. I usually do chunks as individual time slices. With some variables, you can get better compression if you compress multiple slices at once. With some variables, you get worse. The same is true with 2D and 3D. With 3D variables, does it make sense to compress it as a 3D trunk or to do 2D slices? Again, that depends on the variable. I mean, compression really works by finding patterns in the data. So variables that have good correlation, it makes sense to do them in big chunks. But like variables like cloud fraction are extremely difficult to do, and those it makes sense to do smaller chunks. So yeah, did that answer your question?
Yeah, that definitely helps. There's no one answer, it seems. It's very complicated.
Correct.
Yeah.
Correct.
Okay, right.
Correct.
I guess, yeah, it would be, I'd also be interested in seeing sort of what the difference rates are between the different methods for a variable and like different chunk sizes. Because if it's relatively minor, then picking something that performs well might be good enough. But yeah, it'd be good to learn more about that. Yeah.
it's usually minor, except for there's some variables that are just hard. I mentioned cloud fraction because the smallest non-zero, so it's a fraction, so they're all between 0 and 1, but the smallest non-zero value is like order 10 to the minus 12th, I think. So there's a huge range in the data, and it's that stuff like that is hard for the compressors.
Got it. Thank you.
Rich?
Yeah, I was just going to respond to Brian that I put a message in the chat that Haiying about a year ago did some chunking of high resolution impasse data and then parallelizing those chunks to look at the scaling and performance of parallel compression. And I can share her poster that she gave on that topic if you'd like to look at it.
Thanks for that comment. I have a question going back. I think it was your previous slide here on, how we would apply it to CESM. So can you help? I'm having a little trouble understanding this. So is the idea that there would be sort of based on what you find from this, we would kind of pre-specify for different variables the compression, the optimal compression technique for that variable, or is there something else that?
Yes. So I guess if we maybe Alice wants to add something here, but I guess my understanding is if we know what the optimal compression settings are for that variable, then they would sort of automatically be applied. But I guess otherwise we would apply our model to sort of assess what we predict to be the optimal compression settings, and we would have some error checking to account for that.
So if there was,
I guess, can I? Yeah, so I guess like what I'm envisioning is, you have options of all the possible output variables. So hopefully with this tool, we build some kind of database with, all these possible options. And then depending on how someone configures their CSM run and which variables we want to output, then we create this file with knowing that, okay, for this variable, they're using this grid resolution and they're doing daily output. So according to our database, that should be this compression level. And we have all this defaulted in so the user doesn't have to do anything. That's sort of my hope, how this will work.
So extending that to the scenario where someone introduces a new output variable or a kind of time frequency that's different from something that you've like exactly trained your model on, do you have a vision, like would people find a similar variable to specify, or would it be simple enough to run this tool on these new variables by a user? Or?
I mean, on the one hand, it should be simple enough to do, but on the other hand, we know what all the possible output variables are, right, for a specific model. So in theory,
well, like, I guess I'm thinking about like the development.
If you add something
model,
new,
so,
I guess. I guess if you add something new, I don't know the details. This is still all like fuzzy, but I feel that surely there's a way to work this out.
But that is,
go ahead. Yeah,
that is sort of, I guess the whole point of the model is if we introduce a new variable, then we'll be able to accurately predict what the optimal compression settings for that new variable would be.
Cool. Okay, thanks. Thanks. That helps me get a clearer picture. Dave.
Right. Well, so this is sort of a tangential point, but I guess I'm sort of trying to understand where in the process this would go, because currently we're limited to writing out single history slices of our variables. And I assume your compression algorithms operate on the time series output. So that's still an extra stage. So I would assume you would plug this sort of thing in along with the post-processing tool that generates the time series.
I guess that's how I think we would start. But eventually, the netcf files, they could just be compressed as they're written. So if
right, well, the hope is that we're doing, time series file writing on the fly from the model,
right,
but that's not ready to go right now.
Right.
Jim, an update on when that might be a reality, but I don't know the latest on that.
I mean, I guess my thinking on this is the very first thing I like to do is start with data sets that are sitting out there taking lots of space, like some of the lens data sets, and doing a post-processing to them. But certainly going forward in the future, I would hope that we can write the data directly to time series in a compressed format, unless the user specifically says don't compress it.
Yeah, absolutely.
Eric.
So my video seems to be having some trouble, so I won't turn it on. It doesn't show anything. But anyway, thank you for all this. This is exciting work and very important work too. I think this is really vital. The concern I have, I guess, with it is that I think what you're saying is that you have to figure out the optimal mechanism for each variable and also for each resolution of that variable. And I guess potentially, like if you run at paleo, the same variable for paleo climate, you might need something different than for future climate, right? Or is that right? Do you think the time representation might matter as well as resolution?
I think it depends.
Okay,
Again,
sure.
I don't think we know. And the other thing is, we don't have to figure out the optimal for everything. I mean, depending what if you're gonna take your data and then like average it like 10 ways or something, then you might be able to just go pretty aggressive with the compression and you might not really care. So
okay.
I think Brian put something like that in the chat, Brian Dobbins, like you could just go with what you think is a good enough option, or you could just say, I want to be pretty conservative. And of course, there'll always be the option to say, well, these three variables, I want those losslessly compressed. I don't want to lose any information because I'm going to study those to death. But the other 300, I'm not going to look at that closely and go ahead and compress those a lot. I mean, my understanding from
perfect.
Gary Strand with the CSM Lens 1 data is that everyone downloads the same 10 variables and looks at them, and the other 300 are just sitting there taking up space. So we could consider that, okay, for these 10 that everyone really looks at, we'll go very conservative, but for the 300 that people don't really look at, we're going to go more aggressive.
Yeah, that makes perfect sense. Yeah, thanks for adding that in. I'm thinking about all these hundreds of variables that are out there and then trying to figure out the optimal thing for them. But I think you're right that often people don't care. They only care about a few variables and not everything. So yeah, awesome. Thanks for that.
Question kind of following up on that and Brian's comment in the chat about asking about default options is can you give some sense for how bad, let's say we wanted to get kind of started on this sooner rather than later, given the importance of this, like how bad would things be if we did try to pick something sort of default for a lot of variables that was maybe on the more conservative side? Is that even a feasible thing, or is there such a big spread in what the optimal thing is that it really doesn't make any sense to do this default for a lot of variables?
It sort of goes back to that figure that Allison had in her presentation, doesn't it? About I guess the amount of compression we can get. There's sort of a baseline level of compression we can get for most of the variables of about 2 to 1. And I think if we compress all the data at that sort of same conservative level, it would be reasonable to expect that sort of saving.
Was that the 2 to 1 was from lossless, right?
Correct. Yes.
And so if there is there like just arbitrarily, would could you say something like, oh, we can at least get an extra 2-to-1 by using some conservative threshold that for lossy compression that works for every variable or 99% of variables or something like that? Or is there just too much spread in the lossy to be able to do something like that?
I think on average, you could certainly say that. Maybe I think on that plot Alex was talking about, my quote conservative one had an additional about 2x improvement over the lossless one. I mean, all these compressors have different ways of controlling the error too. I mean, in theory, a scientist could just say, well, if every variable has a relative error, if the relative error is, 0.001 between the compressed and uncompressed on every variable, I'm good with that. I mean, we can do things like that too, but we've kind of tried to abstract away the different compressor parameters because they vary by compressor from, what we think the scientists care about. But yeah, I don't think I really answered your question, but
no, that's helpful.
Alex, did you have more to say?
I was actually just trying to remember if there is sort of like a lower limit to how much additional compression we can get. There might have been a couple of variables that we couldn't get any additional improvement over the lossless, but I think for the most part, you could definitely compress to at least say 1.5 times over the lossless. I'm not sure if you could get to 2 for every variable though, but there's definitely some kind of lower bound there.
And I mean, I just want to point out that these are we're being really conservative here, even though I labeled one of them aggressive. I mean, when I hear other people talk about compression, they're talking about, 10x, 20x. And I feel like, okay, people would flip out if we did that, but we're being really, really conservative. And I think that's good because, if we get started that way and then everyone's comfortable with it and finds out, okay, I didn't, there's all of a sudden not global warming because we use compression. I mean, as long as terrible things don't happen, then I feel like we can just crank it up over time and see how it goes.
Maybe just as a communication thing, you could relabel it to conservative, very conservative, and super conservative to
right,
people
exactly.
Don't get scared when they see aggressive.
Probably that's probably good. Yeah, and Brian Dobbins commented in the chat, as far as making this practical, I mean, I recently have been working with Brian so that, because obviously for cloud data, the impact of data storage is immediately obvious in terms of your bill for how much space you're taking up. So Brian and I are starting to work together on some of this compression. I hope the more people can play around with it, the more comfortable people will get, and the more feedback we'll get from the community, and the better this will go.
Cool.
I don't know if you want to say more about that, Brian.
Not yet. Yeah, I'm still very early in this. I mean, my goal is to have sort of, so CSM has this workflow capability that Jim Edwards has added, and we could have a workflow that calls the container that does this. But I'm very, very early on into playing with this, and sort of I've been able to test the NCO stuff in the container on some already time series data, but I want to get the time series generation into that as well, so that it's a full singular solution. So there's still some work to be done, but as soon as I get time and I make a bit of progress, I'll coordinate with Allison and anybody else who's interested, and maybe we can kind of get some eyes on it from scientists and get it in workflows for testing.
Cool. Brian Medeiros, see you with the hand raised.
Yeah, I just have a naive question. Well, I have two naive questions. First, with all of the compressors, do all of the standard, is there any consideration for the end user enabled in expanding it once they go into their analysis programs? Do they need to have software installed to uncompress the data?
So with using the compressors through NetCF filters like we are, then it will just be as if you're reading a losslessly compressed file now. So as long as You have then the right NetCDF HDF5 installation, which obviously we would make sure the right one was on Cheyenne, then it won't be any difference to you.
Okay, great. And then my second question is, say someone might have like a pile of external hard drives filled with hundreds of gigabytes of NetCDF files. What's the first step in just grabbing these compressors and compressing away?
Well, so I mean, for sure, you should already be using lossless compression through NetCF. And then the easiest one to use that I mentioned was Charlie Zender's method, because that's just simply available through the NCO tools. And I wrote a document how to do this, and I shared it with Brian, and I'm happy to share it with you, but it's fairly straightforward. It's no more difficult than applying lossless compression.
Okay, great.
And then the more like the DOE compressors, SC and ZFP, you do have to have a special build of NetCF HDF5, as Jim pointed out in the chat. And also Jim pointed out that, yeah, that you won't have to use NCO for Charlie Zender's tool with the next NetCDF release. It's actually going to be a part of that. So that one, I like that one. You might not get as good compression rates, but it's very simple to use, very easy to understand, and all your tools are going to work automatically. So it has some really great advantages, and I think it's a good place to start.
Sounds good. Thank you.
I see there, we've been talking about compression of output data. I see that there's an interesting comment from Matfei in the chat. Matfei, do you want to unmute and share your thought?
Yeah, I was just wondering because right now you have to download at least 8 terabyte if you want to run like 1850 to 20 something. Yeah, to the end of the 20th century. With Kianet, it's a bit less, but with like Crew and all the other stuff, it's quite some storage space on a laptop.
So particularly for the atmospheric forcings, if you're running with a data atmosphere model.
Yeah.
And so the question being, would it be feasible for us to compress all the atmospheric forcings and other input data to CESM so that people can get compressed input data? That seems like a good suggestion. Makes sense to me. I don't know if others like Jim or Brian or others have thoughts on that, or Allison and Alex, if you've looked at all at input data as opposed to output.
Yeah, I'd be curious to hear. I don't even know, to be honest, whether we use any compression on our input data now, but I'm very interested in this because, again, with the cloud, you have the charges for transfers are related to the size of the data. So if we can do compressed data, it's faster, it's cheaper. That's my interest in this. There are questions, I think, that aren't answered. And Allison and I have talked about doing like a run with restarts compressed to conservative values to see what the variance is from uncompressed runs. Because if you're talking input data, lossless, Jim just responded, input data is not currently compressed at all, not even lossless. Maybe there's something we could do there, but then you maybe don't have that backwards compatibility. But lossy compression would be really interesting to see if there are areas where that's even viable. I don't know. This is a lot to look into. Yeah, it's really cool stuff though. Yeah.
I've kind of steered away from even suggesting using lossy compression on restart files or input files, because my feeling is if that's like a step beyond accepting its use on the output files, and will have much greater effect on the data. So my feeling is let's get the output data that adopted first. But yeah, in the future, it would be fun to look at though.
Mariana?
That's a great question about input data. The question I have is, say we start compressing input data. Do we get rid of the other input data? because then you have two copies. Which one are you going to use? And so it brings a question of backwards compatibility in, because we never overwrite our data.
Given our strong requirement for backwards compatibility, I think we'd have to do it for data sets moving forward, and could start maybe with some of these big data atmosphere forcing data sets that, at least for offline runs, are a big barrier.
I think that could make actually a huge difference in how we store it, even on Cheyenne.
Mm-hmm.
If you're forget about the web servers we have, some of these are particularly as we're going to higher and higher resolution, that could be a really big saving.
Brian Dobbins.
Yeah, I was on this note, I was just going to say, if we, and this is where I don't know enough, but if we can read lossless compression with certain versions of NetCDF, and we can detect that when we reach out to the input data servers, so we can possibly set up a secondary input data servers. Like I said, I'm talking about setting up regional ones for the cloud that have the lossy compression and default back to the lossless from NCAR if that's not available. So I think there are ways to test this and sort of get the lossy stuff out, and maybe track stats as to how many people are still using older versions of NetCDF. You'd have to think of a way to do this, but I think there are some options there, and maybe that's a path forward. Yeah.
Cool. I have a kind of broader question for Allison and Alex, which is, are you able to summarize kind of your sense of the level of support you get versus resistance from the community when you've talked to others about this? And I guess related to that, are there things that others from the software engineering working group can do to kind of support this effort and kind of help you guys see it through to so that we can get this adopted soon, because I know it's an important thing.
Let Allison take that one.
I think certainly the fact that we are going to run out of storage soon has been very helpful in motivating people's interest. GoCon has been extremely supportive. He's actually partially funded a lot of Alex's work. And I feel like people are definitely more interested. I have had trouble getting CAM scientists to look at these data sets that I generated. I'll say in honesty, it's been about a year since I generated them. I have gotten more interest from some of the other groups, and now with the advances in NetCDF compression, we're going to start looking at some of the other model group data. I definitely feel like people are interested, and yeah, it's just, we've been working on this for a long time, but it's really only recently that the technology is kind of coming together that it could be put in practice. And even so, I think the SZ method will work with PNetCDF, but I don't think ZFP does yet. So there's still some issues to be worked out as far as doing it in parallel. But I guess I'm still just aiming for like kind of the low bar of like compressing some of the data sets that are sitting out there, not even worrying about doing it real time or new things, but let's go after some of the old stuff that's taking up space. So that's my thought. But certainly, I mean, I think that this group can definitely make it easier to use lossy compression, maybe make it the default, maybe work with the scientists to help them get experience with the data so that it's not, again, I don't want it to be this scary unknown thing. I want it to be, when they sit down to think about which variables they're going to output. And as Rich mentioned in the comments, that's obviously the best type of compression, is stop outputting stuff that you don't look at. But as you decide what you're going to output, decide, what kind of compression would be appropriate. So that's my 2 cents. I'll let somebody else talk.
Okay, thanks. I see there's a lot of questions and comments in the chat. So let me try to I'm going to try to summarize them, and for the people who asked them, feel free to jump in if I'm misstating these. Cheryl Craig asks about bit-for-bit comparisons, and so I guess this gets to the reproducibility of the lossy compression algorithm itself. So if we have a baseline where we've run lossy compression to store that baseline, and then we rerun code and then apply the same lossy compression algorithm and parameters, will the results still be bit for bit with the baselines? Does that make sense? What I'm asking?
Yes, as far as I know, if you're using the same versions of everything, it should be. There's not inherent randomness in these compressors that we're using, at least.
Okay, good. And Dave Bailey asked, what's the latest on uncompressing to read in terms of CPU time? I think, yeah, so I guess, Dave, you're asking how long does it take to uncompress these files?
So doing it through NetCDF, I haven't noticed a difference between reading a losslessly compressed NetCDF file and one lossy compressed. I mean, it's being taken care of by NetCDF, and you're like, most of your data, I think, is already losslessly compressed. So I don't think you're really going to notice a difference between what difference you already experienced when you went from the original to the lossless, if that makes sense.
Yeah, I guess I was thinking in terms of, using lossless compression on restarts and input data, is that going to add overhead on every time we initialize on a continue or a startup run or whatever?
Yeah, I don't. So the person that probably knows that is Haiying. I don't know the answer to that question.
I kind of do.
Yeah, go ahead.
Because Haiying and I looked last year before I retired from NCAR. We looked at the cost of two different algorithms. One was ZFP, and what is the overhead for the compression and decompression step relative to the overall time it takes to do the IO, and it's algorithmically dependent. Actually, I have a slide or poster that does that, but the effect that you kind of find out really quickly is that your IO times go down when you're dealing with compressed data because there's less of it. So it's actually, if you have a nice decompression algorithm, for example, your read times will be significantly lower if the file's smaller. But the important thing is, like, Haiying never tested this on variable, let's say, all the different algorithms that I know of that were listed by Allison. So some may be more expensive than others, and it's worth looking at the overhead of how, like, per petabyte, how many core hours do you actually have to spend decompressing. David, I could share that poster with you. You could kind of see what I'm talking about. I think another thing is, like, the little subtle thing which crops up is if you try to do parallel, this stuff in parallel and you have a block size, I think the reproducibility issue might crop up if you don't do it with the same block size in two different runs. And I don't know the answer to that.
So that's true. It definitely depends on the block. Like, everything really has to be exactly the same. It does depend on the block sizes. So usually when I do compression, I specifically pick the block chunk sizes for NetCDF so that I know what they are and I don't leave it up to the algorithm to pick.
Yeah, and I think that's that's unfortunate. We try to stay away from that, say an MPI within the models, that you can run with different ranks and you won't get a different answer, but it just may not be possible. But that's a kind of a deep in the algorithm model dimension. There might be a way to patch it up somehow.
Yeah, and Rich brings up a good point, Dave, that it really does depend on the algorithm. Like Charlie Zender's bit grooming algorithm will absolutely be the same time to read data compressed with that as with regular lossless compression, because it's basically like a preconditioning type filter. So the file won't look any different. So we'll take the exact same amount of time. Whereas ZFP and SZ, there's a little additional work that goes on. So, I mean, all of this is very algorithm dependent as well.
Well, Jim raised the issue about HDF5 parallel performance versus PNetCF parallel performance. And I guess my thinking on this is, you know, this is not really an offline process. This is an online thing where we're going to be initializing the model. We're going to be reading in great information, initial data sets, potentially restart files, whatever, things like that. So this is all about the online tools that we have available. And so we need to build it into the whatever the NetCDF reading, writing that we're doing within the model.
I mean, one thing I think that we have to keep in mind too is, I mean, like Rich said, if the file size is smaller, it's going to take less time to read. And the other thing is beyond that, I mean, we're really at the point where storage is so much more precious than CPU hours. So part of me wants to say, who cares if it takes 5 extra minutes at the beginning of the run, if you're going to produce 30 less terabytes of data? I mean, really, who cares, you know? So I think we have to adjust. I mean, I'm being flip about this, but we have to compare the costs of the CPU hours versus the storage, and we have to be willing to take some. We might have to be willing to take some performance hits and certain things in order to reduce the amount of storage.
Well, the people who care about this are like the data assimilation people, you know, who are going to be writing out frequent restarts, and you know, they're going to really care about that sort of performance.
Yeah, and maybe we don't mess with their stuff, you know. I mean, let's go after the low-hanging fruit first.
No, I think your point is extremely valid. Of let's go after the existing data that we have already on disk, you know, because that's a huge burden. And then I think, yeah, it's another question about, as we move forward, how do we better compress our data as we're producing it? So.
Yeah, I was just going to add that with the experiments that we did with the parallel compression, we looked at the cost comparison using some sort of figures of merit for cost of disk space, cost of CPU hours, and it's decidedly on the side of CPU, or decidedly on the side of data storage. And you can kind of express this as to like the concept of, I'm trying to frame this properly. How long would you have to store the data, and how long does reserving that amount of data for that length of time, how much does that cost compared to the CPU cost? Because data is more like renting an apartment, and CPUs are ephemeral, right? So when you look at that, it's the retention time for the data for compressing it from a cost perspective is very small compared to the before you break even. you know. I forget what the number was, but it was on the order of like 48 hours. If you're going to keep the data for more than 48 hours, you probably should compress it. But this is, again, with one algorithm and you know, particular data file. We were using a very high resolution single very high resolution history file. It's like 178 gigabyte file from Impasse. So your mileage might vary, but I didn't get the sense that Allison is wrong. You know, that who cares about the CPU costs, really?
So we just have a few minutes left officially, or a minute or so, but there was a lot of activity in the chat. Do people have some questions or comments that they want to still bring to the whole group, either on this or there was stuff we might have missed from Jesse's earlier talk? So in the last few minutes.
Maybe building on Jim's question here, Allison, are you guys in touch with any of the people that are doing PNet CDF? Do you see that as there's a potential for compression in that? Is that the same stuff you're doing? What's the path forward there?
So I think it's been 4 or 5 years since John Dennis and I contacted PNet CF people. And at that time it was like, well, we don't have the resources to do this unless you have money to give us. And we didn't have money to give them. But more recently, I know that the SZ folks out of Argonne have started working with the PNet CDF people, but I went to their GitHub page the other day and there wasn't a lot there, so I don't know what the status is, but I think it's only good for us if the DOE wants it there, because they probably do have the money to get some of this in there. Yeah, so Jim, maybe you want to comment on that, Jim.
I can only say I don't know either, but I do know that E3SM gave PNet CDF developers quite a bit of funding in the last couple of years, and I think this is on their task list.
I mean, I think the algorithm developers are pretty motivated for this to happen. I mean, I feel like both the ZFP and SC developers would be thrilled if we said, oh, we're going to use your algorithm to compress all our data. So we do have some leverage there, but unfortunately, yeah, somebody has to do the work. So I'm optimistic that all this is going to come around as more and more simulation groups are realizing they need to use lossy compression. So I'm optimistic about it, but yeah.
Okay, any other final questions or comments in this official session before we break for lunch and informal chatting? All right, well, thank you to all the speakers today, and thanks all for this very interesting and useful discussion. Yeah, clearly a lot of interest in the lossy compression, and a lot, exciting to see this continue to move forward. So we are, so this is where we are officially closing the session, but some of us will be staying on for the next hour, in which we try to recreate the experience of chatting and having lunch together. So feel free, please, if you can, stick around and we can chat. I think we're going to set up breakout rooms for that, if I can, if we can figure out how to do that, and so that we can, you can get together with someone you wanted to catch up with, if you'd like. So yeah.
We're going to have enough people left for breakout rooms?
Well, we'll see. If there's only a few of us left, we don't need to, but
yeah, I mean, I got to say, I've been hearing all the conversation. Everything is interesting to me. So I'm unless there are needs, I like the main room.
Okay, well, we could stick here, and then if people want, you can let me know and we can set something up. Cool. I'm going to personally step out for just a few minutes to get myself a little bit of food and take a 5-minute break. But I will be back shortly, and others feel free to stay on and chat.
Hey, Bill, I have a question for you real quick.
Yeah.
So I gave you the hosting before I stopped the recording, so we need to stop the recording real quick.
Okay.
So I can't do it anymore.
Oh yeah, I see this. Okay.
So
I got